This video is a speed run summary of all of the topics in AQA A-level Chemistry paper 1. So that's all of the physical apart from kinetics and rate equations, and then all of the inorganic chemistry topics too. I've cut out as much detail as I can and the video is still huge, but if you do want worked examples or further explanations, I have individual videos covering all of this in much more detail. The first topic in Year 12 physical chemistry is atomic structure, and a lot of this is very familiar from GCSE. You should know that an atom consists of a nucleus containing protons and neutrons, and we call those particles nucleons, and they're surrounded by electrons. The absolute masses and charges of the subatomic particles are incredibly small. Rather than referring to those actual numbers, we tend to talk in terms of atomic mass units and atomic charge units. An atomic mass unit is 1/12 of the mass of one atom of the carbon-12 isotope. You need to appreciate that knowledge and understanding of atomic structure has evolved over time. This hasn't come up a huge amount, but in 2018 we were asked about the differences between the modern model and Thomson's plum pudding model. You should be aware that the plum pudding model has no nucleus and the electrons are not in shells, they're just scattered throughout the atom. And then in 2021 we were asked about Rutherford's nuclear model. This doesn't include protons and neutrons, it just has one undifferentiated nucleus, and then the electrons are not separated out into different energy levels or shells, they all just orbit the nucleus together. We define an element based on the number of protons it has. Any atom with one proton is hydrogen, any atom with two protons is helium, and so on. The number of protons is called the atomic number, and this has the symbol Z because of the German word Zahl, meaning number. The sum of protons and neutrons in the nucleus of an atom is its mass number, and that's A. Mass number is always an integer because for one particular atom, the number of protons and neutrons is always going to be a whole number. For any species, you should be able to identify the number of each subatomic particle. This titanium ion, because it's titanium, must have 22 protons. Then, in order to work out the number of electrons, we look at the charge. Here it's 3+, so we're expecting 3 fewer electrons than protons, so that's 19. And then to work out the number of neutrons, we do the mass number, take away the number of protons, which gives us 26. Isotopes are different atoms of the same element, and therefore they have the same number of protons, but they have different numbers of neutrons. They're chemically identical, in other words, they undergo exactly the same chemical reactions because they have the same electron configuration, but they're physically different because they have different numbers of neutrons, so they may have different melting points, radioactivities, and densities. Unlike mass number, which is for one particular atom, relative atomic mass is a figure which takes into account all of the different isotopes of an element, whether that's in the whole world or just in a particular sample, and also their relative abundances. If we have a lot of a particular isotope, then it makes up a greater proportion of the relative atomic mass than a rarer isotope. We can define relative atomic mass as being the average mass of one atom of that element compared to 1/12 of the mass of one atom of carbon-12. You can also use the same definition, substituting the word mole instead of atom, as long as you're consistent with yourself. There are a few different types of relative atomic mass calculations, starting off with our vanilla GCSE calculate the relative atomic mass. So in order to do this, we're going to take the mass of each isotope and multiply it by the abundance of that isotope. And then we're going to divide our total by the total of the abundances. Now we're going to do a little common sense check. Is that answer between the masses of the isotopes and is it nearer to the more abundant isotope? Our second style of question is similar, but instead of percentage abundance data, we're going to have raw abundance data, which doesn't add up to 100. This means that whereas with the previous question I could have answered it by using decimals, here I need to do the full fraction, and I need to be aware that the denominator of my fraction here is going to be 32, not 100, and this is a really common mistake that we see people making. So I'm going to go through exactly the same process, and then I'm going to do that same common sense check. Is my answer between 14 and 15, and is it nearer to the more abundant isotope? Our third possibility is that rather than being given the isotopes and the abundances, we're given the relative atomic mass and asked to work backwards. So the first thing that we're going to do is to write an expression for what relative atomic mass is, substituting in the numbers that we've got. And here I'm using X as the mass of the isotope because I don't know what it is. So I can then solve that, and I'm going to get an answer for the mass of the missing isotope. Now in this instance, I'm going to find out that I actually have an answer that is not a perfect integer. But remember, mass number has to be an integer, so it's really important that I'm rounding before giving my final answer. To generate the abundance data that allows us to calculate relative atomic mass, we need to use mass spec. And for AQA A-level Chemistry, all you need to know about is time of flight mass spectrometry, not any of the other versions. Mass spec is an analytical technique that allows us to measure the mass to charge ratio of ions. But since the vast majority of those ions are only going to have a single positive charge, this is really basically just giving us the mass. You need to be able to talk through the 5 steps of mass spec. The first step in mass spec is ionization, and depending on the kind of substance that you're trying to analyse, you might use one of 2 different methods. If we have a large molecule like a protein that could fragment easily, then we're more likely to use electrospray ionization. This is where the substance is dissolved in a volatile polar solvent like water or methanol, and then it's injected through a needle that's attached to a high voltage power supply. In that process, each molecule gains a proton, and this gives the final ion a positive charge and an atomic mass 1 unit heavier than the original molecule. Say if we were analysing decane, it's got an MR of 142, so the final ion would have an MR of 143. Alternatively, we can use electron impact ionisation, and this is where we use an electron gun to fire high energy electrons, and those electrons knock another electron off the original substance, and therefore the mass of that new ion is the same as the mass of the original species, but it has a positive charge. Next, all of those ions are going to be accelerated, and this is done by them being attracted to the negative plate, because of course they all have a positive charge. And then they're going to travel through the drift chamber, and that's how they all end up spreading out. And they're going to be detected when they hit the negative plate, and they pick up an electron, and this causes a current to flow. And then the size of this current is directly proportional to the abundance of that ion. If there are twice as many of the ion, we'll see twice as large a current flowing. It's very likely in a question on mass spec that you'll get 5 or so marks for a calculation where you need to work out something like the length of the flight tube, the time taken for an isotope to move, or the mass of a second isotope if you're given the first one. In these questions, they will give you the equation for kinetic energy that you used to have to memorise for GCSE, but they only give it to you in one form. So if you're not very good at rearranging under pressure, it's worth learning the rearranged version with V as the subject. Watch out for the fact that in order to be used in that calculation, the mass needs to be in kilograms, even though you're used to having masses in grams for masses Mr. Mole type calculations. And also be aware that you do need to learn how to calculate velocity, which is distance divided by time. Rather than using numerical data, you could be given a mass spec readout to interpret. Watch out that again this could be abundance values rather than relative abundance values, so they may not add up to 100. Atoms with more than one stable isotope can lead to some funky mass spec data in terms of their molecules. We know that 3/4 of all the chlorine in the world has a mass of 35 and the remaining quarter has a mass of 37. And we also know that chlorine exists as diatomic molecule, Cl2. So the chances that I have a chlorine molecule containing 2 atoms of chlorine 35 are 3/4 times 3/4, which is 9/16. And the chance that I have a molecule made of 2 chlorine 37s is 1/4 times 1/4, which is 1/16. And so the chance that I get a chlorine 35 chlorine 37 molecule is 6/16, and I get a 9:6:1 ratio of the molecules. Electrons occupy fixed energy levels, which we call shells, and the shells can be further divided into subshells called S, P, D and F, the same as the blocks of the periodic table. And each of those can be split up into 1 or more orbitals. An orbital is an area of space where there's a high chance of finding an electron, and all of the orbitals have room for 2 electrons in them. There's 1 s orbital per subshell, 3 p orbitals and 5 d orbitals, and in any given energy level the s orbitals are the lowest energy level. Later we encounter questions about how easy it is to lose electrons, and we always refer to the fact that a p orbital is higher energy than the s orbital. These orbitals also have characteristic shapes. S orbitals are spherical, the p orbitals are dumbbell in shape in 3 different orientations, and then the 5 d orbitals are a clover shape. There are 3 key principles for arranging electrons in atoms. We always work from the lowest energy to the highest energy. For instance, we always put things in s subshells before we put them in p subshells. The second rule is that within any particular orbital, 1 electron spins up and 1 electron spins down. And the third rule is that we don't start pairing electrons in orbitals as long as there are other orbitals free in the same energy level. We're going to put electrons into them separately, and then once they all contain 1 electron, then we can start pairing our first electron. Hydrogen is simple, and then in helium we pair up those electrons. We don't move on to the 2s subshell because it's higher energy, and therefore we're allowed to pair in the 1s subshell. Then in lithium we go 1 up, 1 down, and then we start the new subshell. In beryllium, we again have to pair because the 2p orbitals are higher energy than 2s. Then with boron, we're allowed to start using that 2p subshell, and then when we get to carbon, we don't pair the 6th electron because there's still another orbital which is the same energy as the first 2p orbital. And then likewise, nitrogen, we're not pairing. It's only when we get to oxygen that we start to pair those electrons. There are a couple of little things that might trip you up. The first one is that despite being part of the 4th shell, the 4s orbital is lower energy than the 3d orbital, at least when it's empty, and therefore we put electrons in there before we put them into 3d. However, the presence of electrons in that orbital change its energy level, and that means although it's lower energy than 3d when it's empty and therefore it fills first, once it contains electrons it becomes higher energy than 3d and therefore it also empties first. If you're writing the electron configuration for a titanium atom, then we would have 4s2, 3d2. I'm just using the noble gas configuration here in order to save time. But then when it comes to a titanium 3+ ion, it's going to lose those 2 electrons out of 4s before it starts losing from 3d. It's still left with 1 in 3d. I wouldn't actually write 4s0, but I'm just putting it in so that you can see that they've been removed from there. The other rule that might trip you up is what I refer to as the copper and chromium rule, because these are the 2 elements that you're most likely to encounter it with. We know that atoms are more stable when either all of their d orbitals are full or all of their d orbitals are half full. In other words, having 3d5 or 3d10 is much more stable than 3d4 or 3d9. And therefore, when for instance we get to nickel, we would have 3d8 4s2 because that 4s is filled up first. But then when we get to copper, we take one of those electrons back from 4s and use it to top up the 3d, so that we actually get to 3d10 rather than 3d9. First ionization energy can be defined as the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms of that element to make 1 mole of gaseous ions. It's really important when you write an equation for this that you're including the state symbols. It's also worth emphasising that it doesn't matter what the element is. It doesn't matter if in chemical reactions it forms negative ions or 2+ ions. First ionization energy is always about removing 1 electron to make a single positive ion. You need to be able to explain why we see variation in first ionization energy across the periodic table. The first thing is that there's a general trend as you move from left to right and we see an increase in first ionization energy, and the reason for that is the increased nuclear charge. As we go left to right, each element gains 1 more proton, and therefore there's a stronger electrostatic force of attraction between the nucleus and the outer shell electrons, and that means it takes more energy in order to remove that 1 outer shell electron. The second thing we see is a drop in first ionization energy as we start either a new subshell or a new shell. And the reason for this is that these electrons are in higher energy subshells or shells, and therefore they're experiencing more shielding and they're further away from the nucleus, so they're more easily lost. The third thing we see is a drop for oxygen in period 2 and sulfur in period 3, because the electrons are now being paired in an orbital, and the paired electrons are repelling each other more strongly than unpaired electrons would do, and therefore that is decreasing the amount of energy needed to remove that electron. The amount of substance topic begins with the mole and the Avogadro constant. You should know that the Avogadro constant represents the number of particles in a mole, and that could be atoms, molecules, ions, electrons, literally any type of particle. In all your calculations, you need to give your answer to an appropriate number of significant figures, which is the smallest number of significant figures used in the question. At A-level, we no longer talk about concentration in terms of grams per decimeter cubed, and we almost exclusively use moles per decimeter cubed, but you could still be given mass data and expected to use masses Mr. Mole to convert to moles in order to be able to calculate a concentration. The ideal gas equation is everybody's favourite because you can often pick up 2 marks just for recalling the equation and converting all of the numbers in the question to the correct units. So make sure that you're aware that pressure needs to be in pascals, so you're going to need to multiply it by 1,000 if it's given in kilopascals. Volume is in meters cubed, so you often need to multiply a value in centimeters cubed by 1,000,000, and temperature needs to be in Kelvin, so you may need to add 273 to a temperature that's been given to you in Celsius. Empirical formula is the simplest whole number ratio of atoms of each element in a compound. Ionic compounds have a formula that is already an empirical formula, but for a molecular substance it may or may not be the same thing. For instance, all alkenes have an empirical formula of CH2. To calculate empirical formula from mass data, we're going to start off by using masses Mr. Mole to work out how many moles of each element we have. You rearrange the equation, and then we work out that we've got 0.3 moles of nitrogen and 0.6 moles of oxygen. Then we put those together in a ratio, and we need to convert this to the simplest whole number ratio, which we do by dividing by the smaller of the 2 numbers. I divide the left side by 0.3 and then the right side. Don't fall into the trap of dividing both sides by themselves, because then you'll just get a 1-to-1 ratio. This gives me an answer of 1 to 2, and then I need to express my answer as an actual molecular formula, which here is going to be NO2. To balance equations, start off by writing down the number of atoms of each element on each side. Then look for an element that's not balanced and think about what the lowest common multiple would be. Here I'm going to start with carbon, and the lowest common multiple of 1 and 7 is 7. So I need to multiply by adding coefficients, and here I'm going to add a 7 in front of the carbon dioxide. Next I'm going to think about the hydrogen, and here I'm trying to balance 6 versus 2. So the lowest common multiple is 6, and therefore I need to add a coefficient of 3 on the right hand side. Then I'm going to think about oxygen, and I've got 17 in total on the right hand side. So I need 17 on the left hand side, but I also need to take account of the 2 that are in the carboxylic acid. Once I remove those, I'm left with 15, and therefore I need to add 7.5 as a coefficient for the oxygen. Start answering a theoretical yield question by doing your housekeeping and removing anything that's not part of the question, and then writing down the MR of the other substances. Use masses Mr. Mole to work out what the number of moles is of the substance that you do have the mass for. So here I'm going to find that I have 0.5 moles of sodium azide. Then I need to look at the coefficients to work out how many moles I have of the second substance, and this is probably the most common thing that students leave out when they're doing these calculations. You divide by the coefficient of the thing you already know about and multiply by the coefficient of the thing you're trying to work out. So I've got 0.75 moles of nitrogen. I then go back to masses Mr. Mole to work out that I've got 21 grams. Atom economy is a measure of what proportion of the reactants I started with actually ended up in my useful product, as opposed to in a byproduct that I can't use. Having a reaction with high atom economy is desirable because it's going to save me money. It's going to mean that resources are better preserved, and it's probably going to save energy as well and generally be better for the environment. It's highly likely that you'll be asked to write a balanced symbol equation for something where you haven't been given the formula of all of the compounds. Now, from GCSE, you should be familiar with how to work out the charge on a monatomic ion based on which group it's from, but then you're also expected to recall some compound ions, both what their formula is and also what the charge on them is. That's ammonium ions, sulfate, carbonate, nitrate, and hydroxide. Phosphate isn't actually on the list of ones you're expected to recall, but particularly if you have reactions with phosphoric acid, it's useful for you to know that it exists and also that it has a 3- charge. If we're making an overall compound, it needs to have no overall charge. So to balance the positive and negative charges, look for the lowest common multiple. For aluminium sulfate, the lowest common multiple of the 3+ and the 2- is going to be 6. So to get 6 positives and 6 negatives, we're going to need 2 aluminium ions and 3 sulfate ions. And remember to use brackets around your compound ions in the final formula. In addition to balanced symbol equations, you may be asked to write ionic equations and half equations. We'll look at half equations in more detail when we get to the redox topic, but remember that for an ionic equation, you want to start out with your symbol equation, take any ionic substances and break them down into the ions that make them up. So here that would be iron ions and chloride ions, and then magnesium ions and chloride ions. And if something doesn't change oxidation state between the left and the right side, then you remove it because it's a spectator ion and it doesn't need to be included in the ionic equation. In the first part of the first required practical, you make a standard solution. This could be in the context of a calculation-based question where you're given a particular volume and concentration and you need to calculate what mass of solute you need. In terms of the method, the first thing we need to do is weigh out the precise amount of solute, and we need to know how much solute has been transferred to the solution, not just what was weighed out initially. So either you do the weighing before and after method, or you're going to rinse everything into the beaker that you're using to dissolve the solute in. Then you dissolve that solute using some distilled water, stirring it with a glass rod to make sure that everything dissolves fully, and then transfer this solution to a volumetric flask using a funnel. You need to make sure you rinse down all of the glassware you're using with distilled water and that all of those rinsings go into the volumetric flask. You then add more distilled water until the meniscus rests on the calibration line, and you may need to use a dropping pipette in order to do that accurately. You then stopper your volumetric flask and invert it several times to homogenize the solution. This inversion has to happen right at the very end. It's not something that you're doing earlier to make things dissolve. Then in the second part, you're carrying out a titration in order to work out the concentration of an unknown substance, and that's what's going in your conical flask. Before you start, you rinse through your burette, but you can't do this with water because that would dilute the solution that you're then going to put in the burette. So instead, you rinse the burette with the solution that will eventually be going into it. If you're putting sodium hydroxide in your burette, you rinse it with sodium hydroxide, and this removes impurities and also allows you to fill up the jet space at the bottom. The substance that you don't know the concentration of goes in the conical flask to allow you to swirl it without it splashing out, and you measure that using a volumetric pipette. That's to make your volume very precise and also to reduce uncertainty. If it's an acid-base titration, you include an indicator like phenolphthalein or methyl orange, and these are good indicators because they have a very clear, distinct colour change. You titrate until you see the first permanent colour change, repeating that process until you get concordant data, which are titers that are within 0.1 centimetre cubed of each other. We often use a white tile underneath the conical flask in order to allow you to see the colour change more clearly. All of your volumes are measured at eye level, looking at where the meniscus lies, and your most accurate data is going to be calculated when your burette contains a very dilute solution, because this is going to mean that the volume that you add is larger and therefore the percentage uncertainty is smaller. You use a wash bottle to rinse down the sides of the conical flask and the outside of the burette to make sure that any solution that leaves the burette ends up in the chemical reaction and not stuck to the sides of the glassware. It's fine for us to do this because when we calculate the final concentration, we're going to use the volume of 25 centimetres cubed that we originally put in the conical flask. We're not going to use the volume that ends up in the flask, so even though you're adding water, you're not changing that starting volume that is what's being used in the calculation. To assess the percentage purity of a solid, we can't use regular titration. So what we need to do is a chemical reaction first before we perform that titration, and this whole process is called back titration. So for instance, if I take solid calcium carbonate and I react that with some acid, before I do that reaction I can calculate the moles of acid in that acid. And what I then do is I take the leftovers and I use that in a titration with sodium hydroxide to work out how many moles of acid are still in that solution. The difference between those two numbers tells me how much acid has been used up in the initial reaction with the calcium carbonate. In the bonding topic, we discuss 4 types of crystal structure, which is the overall structure of the substance. Is it ionic like sodium chloride, metallic like magnesium, macromolecular, which you would have called giant covalent at GCSE, like diamond and graphite, or is it a simple molecular substance like ice? Unlike at GCSE, where we made distinctions between bonding types based on whether things were metals or non-metals, at A-level we appreciate that it's a bit more nuanced and really we're talking about differences in electronegativity. Elements that have a large difference in electronegativity experience ionic bonding, and this involves electrostatic attraction between oppositely charged ions in a giant ionic lattice. These substances are solid at room temperature because the strong electrostatic force of attraction requires such a huge amount of energy to overcome. It's likely that you may be asked to compare and contrast an ionic substance with a simple molecular substance, and we get that idea that because we've got stronger forces, it takes more energy to overcome them, and therefore we have a higher melting or boiling point. You could also discuss the fact that ionic substances can only conduct electricity when they're molten or aqueous, and the reason for that is that even though they have charged particles, i.e. ions, in a solid they're not free to move. You definitely do not want to be mentioning delocalized electrons anywhere in a question about ionic bonding. You remember from GCSE that a single covalent bond is a single shared pair of electrons, with double and triple bonds existing when multiple pairs of electrons are shared. You also learned in Year 12 that a coordinate or dative covalent bond is one that contains a shared pair of electrons where both of the electrons have been supplied by one atom. For instance, the ammonium ion is produced when an ammonia molecule with a lone pair on the nitrogen is able to donate that lone pair to a proton that it picks up from solution to make the ammonium ion. You might also have encountered dialuminium hexachloride, which is made when one aluminium chloride molecule and another aluminium chloride molecule are joined together by 2 covalent bonds. This is a perfect example of where at GCSE we would have expected a metal and a non-metal to make an ionic bond, but here we actually see covalent bonding. Giant covalent substances contain thousands of atoms. This includes diamond, which makes 4 strong covalent bonds per carbon atom. Remember, there are thousands of these carbon atoms, and therefore melting it is incredibly difficult and needs a lot of energy. Likewise, graphite also contains thousands of atoms, but these are made into hexagonal layers, or planes as we tend to say at A-level, which are able to slide over each other because there are no strong covalent bonds between the layers. Metals consist of a giant metallic lattice, which is made up of regular rows of positive ions and a sea of delocalized electrons. If you're asked to draw this, you should make sure that you're drawing at least 6 ions. There is a strong electrostatic force of attraction between these positive ions and the delocalized electrons. Metals are able to conduct electricity because the electrons that are delocalized are free to move and carry charge through the metal. In a question about properties, the first thing you want to ask yourself is this comparative or is it just about one substance? If you're asked why A has a higher melting point than B, you need to be talking in terms of it having more energy needed to overcome the forces. But if you're just asked why does A have a high melting point, then you need to be saying it takes a lot of energy to overcome those forces. It sounds like a really pernickety thing, but it will cost you marks in the exam. The second thing you want to think about is what are the forces being overcome, which may or may not be the same thing as what type of bonding it has. If it's an ionic substance, then obviously it's a strong electrostatic force of attraction being overcome. But if it's a covalent substance, you need to think, is this a giant covalent structure, in which case the covalent bonds are being broken? Or more likely, are they asking you about a simple molecular substance, in which case it's the weak intermolecular forces that are being overcome? If I have two methane molecules here, and I'm looking at why does methane have such a low boiling point, it's because the weak intermolecular force is being overcome. The strong covalent bonds inside the molecule are not breaking. Then if you're asked about electrical conductivity, you need to think, does this substance have charged particles, and if so, what are they? Please don't write about delocalized electrons if the question asks you about ionic substances. Then secondly, are those charged particles free to move? And this is where we need to think about the fact that ionic substances can't conduct electricity unless they've been melted or dissolved. We can think about electrons as charged clouds that repel each other, and in trying to get as far apart as possible, these can cause molecules to have different shapes. Remember, it's always the electrons that are repelling each other, not the atoms that they're attached to. When you're trying to decide what to call a particular shape, firstly you need to consider all of the electrons regardless of whether they're lone pairs or bonding pairs, and that number of electrons is going to give you your basic shape. And then, particularly for tetrahedral molecules, you're going to need to actually name the shape based on the bonding pairs only. Linear molecules have a bond angle of 180, and watch out because this one often comes up while you have something that you think has lots of extra lone pairs, but when you're naming it, it's just linear because it only has two bonding pairs. Then trigonal planar molecules have a bond angle of 120, and your basic tetrahedral has a bond angle of 109.5. Trigonal pyramidal has two different bond angles. There are two bonding pairs as far apart from each other as they can be at the top and the bottom, and there's a 90-degree angle between them and the three remaining bonding pairs, which form a sort of tutu around the middle, and the angle between them is 120, just like in the trigonal planar molecule. Then we have our octahedral molecule, which confusingly only has 6 bonding pairs of electrons because the name is based on the 8 faces of the 3D shape, and that has bond angles of 90 degrees. Then we should think about our alternative tetrahedral shapes. If we have one lone pair, then this is going to reduce the bond angle by 2.5 degrees, and we call that triangular pyramidal or just pyramidal. And then we also have our bent or non-linear molecules like water, which have 2 lone pairs. So we remove 2 sets of 2.5 degrees to have a bond angle of 104.5. And the reason for that is because the lone pairs are going to repel each other more strongly than the bonding pairs of electrons. To describe differences in intermolecular forces, we need to be able to talk about bond polarity. Electronegativity is the power of an atom to attract the pair of electrons towards it in a covalent bond. I could say that fluorine is more electronegative than chlorine because it has fewer shells, so there's a stronger attraction between the nucleus and the bonding electrons. Remember, it's those bonding electrons, not just generic outer shell electrons like lone pairs. Now, when atoms differ in electronegativity, that will cause the covalent bond between them to become polar, and it's possible that this may lead the whole molecule to be polar if the molecule is not symmetrical. If you look at my diagrams on the right hand side, here I have chloromethane with this one polar bond, and we have a delta negative on the chlorine to show that it's more negative, and that's the more electronegative atom, and the delta positive on the carbon at the other end. Chloromethane experiences permanent dipole interactions between molecules of the same type. But if you look below that at the tetrachloromethane that I've drawn, even though those individual bonds are polar bonds, because the molecule is symmetrical, they cancel each other out, and we don't have a permanent dipole force between the molecules. There are 3 different types of weak intermolecular force, but before we go into them, you need to understand that the strength of these forces have overlapping ranges. It's not the case that every single molecule that has hydrogen bonds between its molecules is going to have a higher boiling point than every single molecule with van der Waals forces. Something with very strong van der Waals forces could have stronger intermolecular forces than something with very weak hydrogen bonds. Say if you consider a really big polymer, it's not polar, it just has van der Waals forces, but because it's so big and has so many electrons, those van der Waals forces are stronger than the hydrogen bonds that we see between water molecules. Our first and strongest type of weak intermolecular force are hydrogen bonds, and there are 2 crucial things you need to understand. The first is a reminder that this is a weak intermolecular force. We mean the force between the molecules, not the covalent bonds inside the molecules. The second thing is that this arises because of the difference in polarity between hydrogen and three key atoms, fluorine, oxygen and nitrogen. So for hydrogen bonding to arise between two molecules, they need to contain bonds that are polar between hydrogen and one of those atoms. It isn't sufficient for a molecule to have fluorine atoms and hydrogen atoms that are not bonded to each other. The second type of weak intermolecular force is the permanent dipole interaction, and this arises when we have a non-symmetrical molecule that contains bonds that are polar, but not as polar as the ones that lead to hydrogen bonding. For instance, if you have carbon bonded to chlorine, that's a polar bond, and if it's a non-symmetrical molecule, that could lead to a permanent dipole interaction between two adjacent molecules. The final type of weak intermolecular force is the van der Waals force, and this arises because of the random distribution of electrons around a molecule. The larger a molecule is, the more electrons it has, and the more likely it is that just by random chance there's an unequal distribution leading to a temporary dipole on one molecule, and this then induces a dipole on an adjacent molecule, and the attraction between the positive end of one molecule and the negative end of the other leads to the van der Waals force. The larger a molecule is, the more likely it is that this arises, and the stronger van der Waals forces that molecule experiences. Endothermic chemical reactions absorb energy from the surroundings and therefore lower the temperature, and exothermic chemical reactions give out energy to the surroundings overall and increase the temperature. Delta H is the symbol used to denote an enthalpy change, which is a heat energy change measured under conditions of constant pressure. If the value of delta H is negative, this tells us that the reaction is exothermic, and if it's positive, then it's endothermic. We measure standard enthalpy changes at 100 kilopascals and a stated temperature, which is usually 298 Kelvin. Standard molar enthalpy of formation is the enthalpy change, or we would accept heat energy change, when 1 mole of a substance is formed from its constituent elements under standard conditions with all reactants and products in their standard states. You need to be saying all reactants and products, not just saying everything. And then standard molar enthalpy of combustion is the enthalpy change when 1 mole of a substance is completely burned in oxygen, or in other words, burned in excess oxygen, and again, all reactants and products are in their standard states. We don't mention standard conditions here because everything's on fire, so it's not standard conditions. To calculate a standard enthalpy from some experimental data, the first step is to work out how much energy is absorbed or more likely released, and to do this we use the formula Q equals mc delta T. Now in this formula, m is mass, but crucially it's the mass of whatever is changing temperature. If you're doing some flame calorimetry, you're burning a fuel and you're heating up some water, so it's the mass of the water, not the mass of the fuel. Then C is the specific heat capacity, which you're going to be given in the question, and T is the temperature. And because it's a change in temperature, it doesn't matter if that is measured in degrees C or in Kelvin. For the second required practical, you measure an enthalpy change, and the one that is recommended is dissolving copper sulfate. We do this in a polystyrene cup in order to minimise energy losses to the environment. And before you start, it's really important that you take the temperature at regular intervals for a long enough time, usually 4 or 5 minutes, and this is to establish an accurate starting temperature and to make sure that the temperature of the water wasn't changing before you did anything to it. Then we need to dissolve the copper sulfate in the water, and it's important here that we have to use the weighing before and after method. You can't use the rinsing method because in order for us to calculate an accurate enthalpy change, we need to have a known mass of water and it all needs to be interacting at the same time, so you can't use rinsing. Weigh the weighing boat with your copper sulfate in and then pour it out, and weigh that weighing boat afterwards to see how much copper sulfate was transferred, because there may be residue. Measure the temperature over several minutes, maybe up to 15 minutes, and then plot the temperature against the time, and you're going to draw 2 lines of best fit. One for your initial readings, where it's just the water, and then one after you added the copper sulfate. You then extrapolate both of those lines of best fit back to the point where you added the copper sulfate, and the difference between them is the temperature change. You can use that information together with Q equals mc delta T to calculate the overall energy change. We're then going to convert that number, which is in joules, to kilojoules by dividing it by 1,000. And what we're then going to use the mass of the copper sulfate for, as opposed to the mass of the water, is to work out how many moles of copper sulfate were added so that we can work out an enthalpy change per mole. So you take Q, which you've converted into kilojoules, and you divide it by the number of moles, and that's your delta H value. Hess's law tells us that the enthalpy change for a reaction is independent of the route taken. Questions may ask you to work out an overall enthalpy change, or give you that overall enthalpy change and ask you to work backwards from that to work out one of the intermediate steps. I would always draw a Hess's cycle because it's much easier to pick up working marks for a cycle than it is for a mathematical expression. The first thing you need to do is look at your table of enthalpy change data and decide is each one combustion or formation data, and then write an equation for each one of these processes. Now that I've got these expressions, it's much easier for me to draw my cycle because they tell me which way my arrows need to go. Here I'm going to be making carbon dioxide, and I can add in my 2 arrows, and I know which way they're going because I can see from the equations I've already written. Then I can add numbers onto those arrows, and I need to watch out for the fact that although in this instance I've only got 1 of each, if I have multiple moles of a particular substance I may need to multiply up those values. Then I'm going to write start and end on either end of the arrow that I'm going to try and work out the value of, and draw a new arrow that goes from start to end but going the whole way round the rest of the cycle. This is going to help me see, am I going the right way up arrows or the wrong way up arrows? Here I'm going the right way down the -393 arrow, so I keep that number as it is, but I'm going the wrong way up the -283 arrow, so therefore I need to flip the sign or just add another minus, and I can work out that the overall enthalpy change for this reaction is -110 kilojoules per mole. When we define mean bond enthalpy, this is the amount of energy required to break 1 mole of the stated bond because it's a standard enthalpy change. But this is also averaged across a range of compounds that contain that bond because there isn't one gold standard value for how much energy it takes to break a carbon-oxygen bond. It depends upon the context of the rest of the molecule. This leads to differences between experimental data for one compound and the databook. You may be working out the energy change for a reaction based upon some bond enthalpy data. We need to add up all of the bonds that are going to be broken and subtract from that all of the bonds that are going to be made, and the difference between those two numbers is the overall enthalpy change. If it's negative, this shows you that the reaction is exothermic, and if it's positive, then it's endothermic. It's much more common that you'll have a situation where you're told what the overall enthalpy change is, and you need to work backwards to figure out the value of a particular bond. If you do a quick sketch of the different molecules, this allows you to cross out the bonds as you include them, and it saves you from forgetting to include a coefficient. Here we write an expression for all the bonds on the left, take away all the bonds on the right. If you've got a reaction where not all the bonds actually need breaking, then it's up to you whether or not to include these ones. Both versions will be in the mark scheme. Once we've written out this expression, we can start to simplify it. Make sure that you've got extra brackets around everything on the right hand side because very commonly people will take away that first set of bonds and not the 4x. Then we can simplify this down further, and one thing that's worth pointing out is that the final mark of this calculation is for finding out one of the bond. So even if you have a complete brain melt and you can't remember how to get through the rest of the calculation, if you've done something that involves all of the numbers that you've been given and then you divide by the appropriate number, you can still pick up a mark there. Since kinetics isn't included in paper 1, we move straight on to equilibrium and the Chatelier's principle. This applies to reversible reactions, which you can identify because they contain the reversible reaction arrow. At equilibrium, the forward and reverse reactions proceed at equal rates, and this means that the concentration of the reactants and the products remains constant. It does not mean that they are the same as each other. We can use Le Chatelier's principle to make predictions about the impact of changing temperature, pressure, or concentration. In the first line of your answer, say that the system will shift to counteract the change. Although unlike at GCSE, where that statement on its own would be enough, you need to make sure that you include what the change is. For instance, saying the system shifts to counteract the increase in temperature. Next, include which reaction is being favoured and why that's the case. For instance, we might favour the endothermic reaction because we're trying to reduce the temperature after a temperature increase. Or it might be that the side with fewer molecules is favoured because we're trying to reduce the pressure after it's been increased. Thirdly, specify which side the equilibrium moves to. If you're favouring the forward reaction, it's moving right, and if the reverse reaction is favoured, equilibrium is moving left. Finally, describe what the impact on the yield will be. Remember, adding a catalyst does not affect the position of equilibrium or how much product you make. The reason for this is that the forward and backwards reactions are both going to be sped up by the same amount. The reaction will reach equilibrium sooner, but the overall concentration of the product will be the same. You need to be able to write a Kc expression for systems where everything is in the same phase, so either everything is a gas or everything is a solution. The first thing you need to be able to do is write an expression for Kc. We're using concentration, which we show using square brackets. The products go on the top of the expression and the reactants are the denominator, and the coefficients in the symbol equation are going to become the powers in that expression. In order to work out the units, we start from the base unit of moles per decimeter cubed because all the concentrations are measured in that. You could choose to write it out for every single thing in the expression and then cancel them out, or you can look at your symbol equation. So here we've gone from 4 moles on the left to 3 on the right, so we've had a decrease of -1. So if we put moles per decimeter cubed to the power of -1 and we solve that, then we eventually get the right units. One mistake that we regularly see from students in equilibrium questions is that they put numbers into this Kc expression that are not actually concentrations. So you've usually already worked out the number of moles of something, and you need to turn that into a concentration by dividing it by a volume. Often, before we can substitute concentrations into a Kc expression, we're going to need to work out the number of moles at equilibrium. So we'll be given something like this, where we're told the starting moles of two of the substances and also the end moles of one thing. So the easiest way to get around this is to draw what I call an ice table. So you're going to think about the initial moles and also what you've got at the end. So if I look at A, I can see that A has decreased by 0.3. And then I can use the coefficients in the equation to tell me how much everything else has changed by. And that will allow me to work out the final moles of all of the different substances. I then need to take that data and go on to calculate concentration for each one. We then move on to redox reactions, and you know from GCSE that oil rig exists, so oxidation is loss of electrons and reduction is gain of electrons. But in year 12 we learnt that oxidising agents oxidise other species by accepting their electrons, and reducing agents reduce other species by donating their electrons. Oxidation states are a numerical way of representing how electrons move within redox reactions. To work out the oxidation state of any element, there are a certain number of rules that you need to have memorised. The first one is that elements always have an oxidation state of 0. From that point onwards, the rule is that if two rules contradict each other, you always go with the most electronegative element. So first up, fluorine. Fluorine is always an oxidation state of -1 in a compound. Oxygen is -2 unless it's either bonded to fluorine, in which case that rule takes precedence, or if it's in a peroxide where it has an oxidation state of -1. Chlorine has an oxidation state of -1 unless it's bonded to something more electronegative, so in which case that rule takes precedence. Hydrogen is +1 unless it's in a metal hydride, in which case it's -1, and group 1 metals are always +1. Unlike in a symbol equation or an ionic equation, for a half equation we're only interested in one particular element, although we are going to have to include hydrogen and oxygen to make it work out. Your first step is to identify which element is changing oxidation states and make sure that element is balanced. In this example, the manganese is already balanced, but particularly if you're working with non-metals, you may have a situation like this chloride ion discharging where you need to add a coefficient in order to make these things work out. Next, I'm going to add water molecules in order to balance out the oxygen that I can see on the left-hand side. And then I'm going to balance out these 8 hydrogens I've just added by 8 hydrogen ions on the left. Now I need to add electrons, so I've got a 2+ charge on the right hand side, and on my left hand side I've got a minus and 8 pluses, so that gives me +7, so therefore I need to add 5 electrons. You may also have been taught to do this by looking at the oxidation states, so we could say that on the left here we've got +7 and on the right we've got +2, so that will need to be balanced out by those 5 electrons. If you're going to combine two half equations, you need to have the same number of electrons overall. Here I've got 5 on my left hand side and 2 on my right hand side. So the lowest common multiple of those would be 10. And so I'm going to take this first equation and times it by 2, and the second equation and times it by 5. So now I'm able to cancel out the electrons, but I'm also able to cancel out some of the hydrogen ions. So I can replace that one there with 6 hydrogen ions that haven't been cancelled out. And now I'm just going to join these two equations together to produce an overall equation that looks like this. In the first topic of inorganic chemistry, we learned that elements can be classified as belonging to the S block, the P block, the D block, or the F block, based on where they're found in the periodic table. And this in turn is determined by their proton number and which subshell their highest energy electrons are found in. Next, we look at some general trends across the periodic table, using period 3 as our model for it. So the first trend is that as we go left to right across the period, the atomic radius decreases. And the reason for this is that we're increasing the number of protons and therefore the nuclear charge. And this means that the strong electrostatic force of attraction between the nucleus and the outer shell electrons gets stronger. There aren't any more shells, everything in period 3 has 3 shells, so we're not having any increase in shielding, so it's just the nuclear charge that is affecting the radius. Even though we've already discussed first ionization energy, I'm going to take the opportunity to remind you again that these state symbols are crucial and you won't get the mark without them. You need to be able to describe that as we go left to right across the table, the first ionization energy in general gets higher because of the increased number of protons, with a couple of key exceptions. Firstly, when we get to aluminium, our highest energy electron is in the 3p subshell, which is higher energy than 3s, so we see a small dip, and then we see another dip when we get to sulfur, because here we have electrons being paired, and they are going to repel each other more than the other electrons already were, and so therefore it's going to be easier to remove that first electron. In order to describe differences in melting point across period 3, we need to think about what kind of crystal structure we have. So sodium, magnesium and aluminium are all examples of metallic structures, where silicon is giant covalent, and then phosphorus, sulfur and chlorine are simple molecules, and argon of course is monatomic. The second question to ask yourself is, what is the force that's being overcome in order for this substance to melt? So for the metallic substances, it's a strong electrostatic force of attraction between the positive ions and the delocalized electrons. For the giant covalent structure, it's covalent bonds. And for the simple molecular substances and also the monatomic noble gas, it's going to be van der Waals forces. You could be asked to compare two substances from two different categories, say a metallic one and a simple molecular one, but you could also be asked to make comparisons within a category. So for instance, we can say that magnesium has got a higher melting point than sodium because it's got higher charged ions and also it's got more free electrons to make that bond. Likewise, if we look at our simple molecular substances, we know that phosphorus makes a P4 molecule, sulfur makes an S8 molecule, and chlorine makes a Cl2 molecule. And this is reflected in their melting points as well, because those molecules have more or fewer electrons and therefore stronger or weaker van der Waals forces. The alkaline earth metals are found in group 2 of the periodic table, which is part of the S block. They have 2 electrons in their outer shells and therefore they make 2+ ions, which is important for you to remember when you're creating symbol equations involving them. Because they're metals, they conduct electricity and they conduct heat. As you go down group 2 from beryllium to barium, the atomic radius gets larger. This is because the impact of adding another electron shell is much greater than the impact of the additional nuclear charge from the extra protons. Linked with this is the trend in first ionisation energy. As you go down the group, the energy required to remove the first electron decreases, because the ions are getting bigger, and this means that there's a weaker force of attraction between that outer shell electron and the nucleus. The melting point also decreases as you go down the group, from about 1300 for beryllium down to about 700 for barium. Again, this links back to atomic radius. The atoms or cations are getting bigger, but there isn't any change in overall charge. They're all 2+ charge ions. And so that means that that charge is kind of more spread out. And so this means that overall the charge density decreases, and therefore the strength of the attraction from the ion to the electrons also decreases. As with all metals, the group 2 metals get more reactive as you go down the group, because the outer shell electrons are more easily lost because they're further from the nucleus and they experience more shielding due to the greater number of shells. You need to be able to write equations for the reactions of group 2 with water, and in the case of magnesium there are different equations for steam and for liquid water. So for steam, we're going to have our solid magnesium with our gaseous water, because it's steam, reacting to make magnesium oxide and hydrogen, and you're going to observe a bright white light, just as you do if you make magnesium oxide by putting magnesium in a Bunsen burner. Then when magnesium, calcium, strontium and barium react with liquid water, it's acting as an oxidizing agent. So the magnesium is going to react with liquid water to make magnesium hydroxide and also hydrogen gas. That magnesium hydroxide would be a solid because magnesium hydroxide is sparingly soluble, so it's not really going to go into the solution. We know it's a tiny bit soluble because the pH is going to change by a tiny amount, but not by nearly as much as we would see if we had, say, calcium hydroxide, which is soluble and therefore would have the state symbol AQ. Calcium hydroxide is a colourless solution, but you are also going to be able to see some bubbles or effervescence from the hydrogen gas. The group 2 hydroxides get more soluble as you go down the group, and we can identify this by looking at the impact on pH. As we've just mentioned, magnesium hydroxide is only sparingly soluble, so a solution of magnesium hydroxide might only have a pH of 8 or 9, compared to a solution of barium hydroxide, which could be as high as 13 or 14. In terms of their uses, magnesium hydroxide is put in indigestion tablets in order to neutralise excess stomach acid, and calcium hydroxide is used by farmers to neutralise acidic soils in the fields where they're growing crops. Now, in contrast to the hydroxides, sulfates get more soluble as you go up the group. So the one to remember is barium sulfate, which is used in barium meals. In other words, it's used as a radiographic contrast agent. So if you're trying to take an X-ray of someone's intestines, they eat the barium meal, and the barium sulfate will reflect their X-rays in the same way that bone would. It's safe to do this even though barium sulfate is incredibly toxic, because it won't dissolve in the body's fluids and therefore it can't be taken in. Barium chloride is also used as a test for sulfate ions. So the barium ions from the barium chloride will combine together with any sulfate ions that are in a solution to make a white barium sulfate precipitate. When we do this test, we acidify it first, usually using hydrochloric acid, because that way we're only adding chloride ions, which are in the barium chloride anyway. And the reason we do that is to remove any carbonate ions, which would give a false positive in that they would also generate a white precipitate. Titanium is a really important metal because it's so lightweight, and so it's used for things like making jet planes. In order to extract it, we take an ore called rutile and heat this with chlorine and coke to turn titanium oxide into titanium chloride. And then the titanium chloride can be further reduced using magnesium, or in fact sodium, as a reducing agent, in other words, an electron donor. So you should be able to write symbol equations for that process as well. Sulfur dioxide, which is responsible for sulfurous acid, which causes acid rain, can be removed from waste gases from a power station by an acid-base reaction with calcium oxide. Basically, we spray a slurry into the gases that contains these calcium-based compounds, and this removes the sulfur. Finally, we have the halogens, which are found in group 7 in the P block and all have 7 valence electrons. Just like group 2, as we go down the group, we're going to see that there's an increased atomic radius because we're adding a new shell each time. Electronegativity is the tendency or power of an atom to attract a pair of electrons in a covalent bond towards itself, and fluorine is the most electronegative element in the whole periodic table, with electronegativity then decreasing as we go down the group. This also means that as we go down the group, things become steadily less good oxidizing agents, so fluorine is a very good one, astatine is a much poorer one. The reason for all this is this larger atomic radius, including more shells. So this means that the outer shell electrons are experiencing more shielding, and therefore there's a decreased attraction between the nucleus and the bonding electrons. And this is really important. You need to be talking about the bonding electrons, not just outer shell electrons in general, because electronegativity is about attracting electrons that are in a covalent bond. This also means that the bond polarity decreases as you go down the group, so we know that when fluorine bonds, it makes very polar bonds often, and also this is going to mean that the bond strength also changes. In terms of the boiling points, we know that fluorine and chlorine are gases, where bromine is a liquid and iodine is a solid. And so all of these small covalent molecules are experiencing van der Waals forces. But because bromine and iodine are larger atoms and they make larger molecules that have more electrons, the van der Waals forces are stronger. This means that they take more energy to overcome, and therefore iodine is going to have a higher boiling point than bromine, and bromine higher than chlorine, and so on. The more reactive higher up halogens are able to displace the less reactive lower down halogens from their compounds. So for instance, chlorine in the form of chlorine water can displace bromine from potassium bromide. Chlorine water is a very, very pale green, almost colourless, and in this reaction we would see an orange solution forming as the bromine water formed. If we repeated this process with potassium iodide instead, we'd see a darker brown solution forming. You also need to be able to write ionic equations for this, in which case we would remove the spectator ions and just not include the potassium. And you also need to be able to write half equations too. When sulfuric acid reacts with solid sodium halides, it can perform two different roles. Firstly, it acts as a proton donor or an acid. So if we have some sodium chloride reacting with sulfuric acid, we make steamy white fumes of hydrogen chloride and also some sodium hydrogen sulfate. And this process will happen for any of the halides, and they're all just functioning as bases. But then if we think about bromide ions and iodide ions, which are the best reducing agents, then the reaction is able to go a little bit further with the acid acting as an oxidizing agent. This won't work for fluoride ions or chloride ions because they're not powerful enough reducing agents. So if we take hydrogen bromide that was formed in the first reaction, this can be split up into hydrogen ions and bromide ions, and these can react further with the sulfuric acid to make some bromine and some sulfur dioxide and some water. And you can see here that the sulfur is moving from a +6 oxidation state to a +4 oxidation state, so it's being reduced and acting as an oxidizing agent. Now in this process we make this sulfur dioxide, which we can't see, but because the bromine is produced at the same time, this makes the fumes turn brown. And then if we think about the iodide ions, we have a slightly different process. So we have these 8 electrons here, they're coming from the iodide ions, 8 of them being oxidized to produce 4 iodine molecules and also these 8 electrons. And this can happen because iodide ions are an even stronger reducing agent than the bromide ions. You can test for the presence of halide ions in solution by using acidified silver nitrate solution. We acidify using nitric acid to begin with because this will remove any carbonate ions from solution, and these would lead to a false positive because they would also give you a white precipitate. When you add the silver nitrate, silver fluoride would be produced if you had fluoride ions, but this is soluble, so there isn't an observable change. Whereas silver chloride will produce a white precipitate, and you should be able to write an ionic equation for this, showing how the two soluble ions form together to make this insoluble precipitate. So silver chloride is a white precipitate, silver bromide is cream, and silver iodide is yellow. And if we wanted to analyse those further, say look at how much was made, we could filter them out of the solution because they are insoluble. Now, if you produce just silver chloride or silver bromide in isolation and you don't have anything to compare them to, it might be hard to say whether it is white or cream. So we can identify this further by adding dilute ammonia, because silver chloride will redissolve in that dilute ammonia, but silver bromide will not. Small, carefully controlled amounts of chlorine are added to both drinking water and swimming pools in order to kill harmful microorganisms, despite the fact that chlorine is toxic. This is because, on balance, the health benefits about not having pathogens in that water outweigh the risks of adding a small amount of a toxic substance. Chlorine can react with water in two different ways, depending on whether sunlight is available or not. When there's no sunlight, we see the chlorine reacting with water to make two different acids, hydrochloric acid and chloric acid. This is described as a disproportionation reaction because the chlorine is both reduced and oxidised, going from an oxidation state of 0 in chlorine to -1 in hydrochloric acid and +1 in chloric acid. And we can describe these processes using half equations. In the presence of sunlight, we see a different reaction being undergone, and as well as hydrochloric acid, we also have the production of oxygen gas. When chlorine reacts with cold, dilute aqueous sodium hydroxide, it produces two major products, sodium chloride and sodium chlorate. Going from the oxidation state of 0 in the elemental chlorine, in the sodium chloride, the oxidation state of chlorine is -1, and in chlorate, it's +1. So this is another example of a disproportionation reaction. This is sometimes referred to as sodium chlorate 1 to differentiate it from sodium chlorate 5, which we'll get to in just a second. So we have two major products here, and the sodium chlorate can be used for a variety of things, including making herbicides, explosives, dyes, cosmetics, pharmaceuticals, and paper. Then if the sodium hydroxide is hot, we have a different reaction going on, but this one is still a disproportionation reaction. So this time we have sodium chlorate 5, where the chlorine has an oxidation state of +5 instead. And then the very last thing in paper 1 of AQA A-level Chemistry is the fourth required practical, which is a series of test tube reactions to identify cations and anions. Now we've gone through most of this already, but just to recap, we can identify which group 2 ion is present by looking at the solubility of their hydroxides and their sulfates. So if we add sulfuric acid, we're going to make a group 2 sulfate, and whereas barium sulfate is highly insoluble and forms a white precipitate, magnesium sulfate is very soluble, and so we would just see a colourless solution. If we think we might have ammonium ions, then we add sodium hydroxide and warm in a water bath so that ammonia gas would be given off. And then we test those fumes to see if they are ammonia gas with damp red litmus paper, which will turn blue in the presence of ammonia. As we've said, to identify group 7, we use acidified silver nitrate, which will form a white precipitate for chloride ions, a cream precipitate for bromide ions, and a yellow precipitate for iodide ions. And we can then also try to dissolve those precipitates using dilute ammonia, and the silver chloride precipitate will dissolve, but bromide wouldn't dissolve. If we think we might have hydroxide ions, of course, those are what are found in alkalis, so we can do some kind of pH test, usually red litmus paper, which would turn blue. To test for carbonates, we can add any dilute acid and we would see effervescence, and if we really wanted to be sure, we could test that effervescence with lime water, which would turn cloudy if it was carbon dioxide being given off. And finally, to test for sulfate ions, we use acidified barium chloride, which will form a white precipitate. Thermodynamics is the science of heat. Often within thermodynamics, we'll be discussing enthalpy changes, which are changes to heat energy happening at constant pressure. Often these will be standard enthalpies, in which we're either making 1 mole of a substance or using up 1 mole of a substance. Some of these enthalpy changes, such as enthalpy of formation, are measured under standard conditions, and we tend to assume that the pressure is 100 kilopascals, and if the temperature isn't explicitly given, we assume 298 Kelvin. We start with two definitions that you learned in Year 12, but that are still necessary here. Standard enthalpy of formation is the enthalpy change or heat energy change at constant pressure, when 1 mole of a compound is made out of its constituent elements. Those are just the elements that are included in that compound, under standard conditions, so 100 kilopascals and 298 Kelvin, with all reactants and products being in their standard states. Remember, you need to say all reactants and all products, not just everything. We can represent this with a chemical symbol equation like this. Note we're making 1 mole of water, and water is a liquid, whereas oxygen and hydrogen are gases. As we saw in the energetics topic, both delta HF and delta FH are normal creditworthy ways of denoting this. Then standard enthalpy of combustion is the enthalpy change or heat energy change when 1 mole of a substance is completely burned in oxygen, or you might say burned in excess oxygen, with all reactants and products being in their standard states. Here we don't say under standard conditions because this is combustion, so it's not standard conditions, the temperature is going to be much higher. Standard enthalpy of atomization is the enthalpy change when we make 1 mole of gaseous atoms from an element in its standard state. There are 2 different ways that this can happen. If we're thinking about a metal, then all we're going to be looking at is a state change from a mole of solid atoms to a mole of gaseous atoms. But if we have a molecular substance, then that molecule needs to break apart. And this is where people start to get a little bit confused, because you need to remember that atomization will make 1 mole of gaseous atoms. It doesn't matter how many moles of molecules we start with. So in order to make 1 mole of gaseous atoms, you're going to start with half a mole or a quarter of a mole or an eighth of a mole of the molecule. You met first ionisation enthalpy in year 12 as part of mass spec, so you know that this is the standard enthalpy change when a mole of gaseous atoms loses an electron each to form a mole of gaseous ions. Remember, it doesn't matter what type of ion an atom would usually make in a chemical reaction. Here we're always removing that first electron. After the first ionisation energy come the second and third and fourth, and in each instance we're just removing 1 electron and increasing the charge by 1. First electron affinity is measured when electrons are added onto gaseous atoms or negative ions. Just like with ionisation energies, we don't have 1 electron affinity, we have subsequent ones if an atom is able to receive more than 1 electron. The first electron affinity of a non-metal is going to be exothermic, while the second or third will be endothermic, because we're adding an electron onto something that is already negatively charged, and that negative ion is going to repel the new electron that's being added. Their lattice enthalpies of formation and dissociation are inverse processes of each other. So the exothermic process of lattice formation is the direct inverse of the endothermic process, and so the 2 enthalpy values will be the same magnitude but with different signs. Lattice formation is the standard enthalpy change when 1 mole of solid ionic compound is formed from its gaseous ions, and this is often what we're trying to work out when we construct Born-Haber cycles. To write an equation, I need all of the relevant ions in a gaseous state joining together to make 1 mole of ionic solid. You should be aware that the most exothermic lattice formations occur for small, highly charged ions, as these have a higher charge density. When you discuss the values for lattice formation, be sure to say more or less negative or more or less exothermic. Don't say bigger or smaller, as this is ambiguous when dealing with negative numbers. Students are often confused by enthalpies of hydration and solution because they do sound very similar. The enthalpy change of hydration is when water molecules surround 1 mole of gaseous ions, and this is going to apply to a specific element, so you need separate values for each element in the compound. We use AQ for water because this isn't water that's taking part in a chemical reaction, it's just making the ions aqueous. The standard enthalpy of solution is that much more realistic everyday process where 1 mole of an ionic solute is dissolved completely in enough water that the ions are no longer interacting with each other, and this is going to be 1 value for the compound rather than each element independently. Mean bond enthalpy is the heat energy required to break 1 mole of covalent bonds, and it's averaged across a range of molecules. Hess's law tells us that the enthalpy change or heat energy change at constant pressure for a reaction is independent of the route taken, and Hess's cycles allow us to make predictions about enthalpies that are difficult to measure directly. The Born-Haber cycle is a really specific version of a Hess cycle, and it's applied to an ionic solid. It allows us to calculate the lattice enthalpy of formation by using ionisation energy, electron affinity, enthalpy of atomization, and enthalpy of formation. Born-Haber cycles allow us to predict the enthalpies of formation for theoretical compounds that don't exist yet, and it allows us to predict whether these compounds will be stable and actually likely to exist in the real world. To construct our Born-Haber cycle, we start by taking the elements in their standard states, and this will be the second rung of the Born-Haber ladder. Any exothermic processes in this diagram with negative enthalpies are represented by arrows going down, and endothermic processes with positive enthalpies are going to be represented by arrows pointing up. So firstly, we're going to make our ionic compound. This is standard enthalpy of formation, which is delta HF. It's an exothermic process, so that arrow points down. Next, I need to turn both elements into gaseous atoms, and it doesn't matter which order I do these in, but I tend to always go metal first. So there's my standard enthalpy of atomization for magnesium, and then the next one tends to be the first point that things go wrong, because people forget that standard enthalpy of atomization is to make 1 mole of atoms, and here we're making 2. So my value will be double the value listed in the data table. Then I need to think about gaining and losing electrons in order to form ions. So we start with the first ionization enthalpy of magnesium. Don't forget to include the electron. Don't just have your single positively charged ion and no electron. Everything needs to still balance. And then we're also going to remove a second electron from each magnesium ion in order to produce these magnesium 2+ ions. Now, each electron that has been produced can then be given to a chlorine atom to make a chloride ion. So this is going to be our first electron affinity. And what we need to remember here is that this is going to be an exothermic process, so the arrow is pointing down, and also that we're doing it twice because we have 2 moles of chlorine atoms. So again here we need to be doubling. And then finally, our mole of gaseous ions of magnesium and our 2 moles of gaseous chloride ions can join together to form a mole of our solid ionic compound, and this is the enthalpy of lattice formation. The next step is to look through the data table and assign a value to each one of these arrows. Whether it's a really simple Hess's cycle question or a more involved Born-Haber cycle, I like to write start and end at either end of the arrow that I'm trying to figure out the value for, and then link them up, because this is just a really quick and easy way to make sure that in the stress of the exam you don't accidentally go the wrong way around the cycle. So each time that I'm going the wrong way up an arrow, I'm going to take the negative of that number. So I'm going to end up with the negative of 2 lots of -349, the negative of +1450, the negative of +736, the negative of 2 lots of 122, the negative of +150, and then this final arrow I'm going the correct way down, so I'm just going to add it on, and that's going to give me an overall value of -2524 kilojoules per mole. In part 2 of the thermodynamics topic, we encounter the concept of Gibbs free energy and the calculation which refers to enthalpy, temperature, and entropy. Entropy is a measure of how random or disordered a system is, and everything is always tending towards greater entropy. So the only way that we can avoid that is if we're putting in work or energy. Now, all entropy values are greater than 0, they're all positive, but an entropy change can be negative. As a general rule of thumb, if a chemical reaction leads to an increase in the number of particles, this increases entropy and gives us a positive entropy change. And an example of this would be the chelate effect, which we see in the transition metal topic. Likewise, a state change where we have a gas rather than a solid, or a chemical reaction which produces gaseous products, is going to lead to an increase in entropy. Every chemical has a value of entropy, and we can use these to calculate the entropy change of a reaction where we subtract the reactants from the products. So for instance here we start off thinking that water is 189 and there are 2 moles of water, so we would double that to give us a total of 378, and then hydrogen is 130, so 2 moles of that would be 260, and then we add on the 205 for oxygen, so that gives us 465, and then 378 take away 465 gives us an entropy change of -87, so we're getting less entropy because actually this is becoming more organised. It's important when we put these values back into the Gibbs free energy equation that we bear in mind that entropy is calculated in joules per mole per Kelvin, but delta G and delta H are in kilojoules per mole. So you need to convert your entropy data before you can use it in this equation. A typical Gibbs free energy equation is likely to ask you whether a reaction is feasible. So feasible reactions favour the formation of products under the conditions where the reaction is actually happening. They're not all fast and they're not all exothermic, but Gibbs free energy is a value that we can calculate to predict whether that reaction is spontaneous or not. And when we say free energy, we mean energy that is available to do work as opposed to energy that's stored and locked up somehow. When delta G is less than 0, the reaction is feasible. When it's greater than 0, it's not feasible. And crucially, the point at which it's exactly 0 is when it becomes feasible. So we're going to use this a lot in our calculations. Lots of Gibbs free energy questions will ask you to work out the temperature range where the reaction is feasible, and this might be phrased as a standalone question where you have to do all the work, or they might break it down into asking you to work out the entropy change and maybe even giving you some mean bond enthalpy data so you can work out the enthalpy change. But regardless of how the question is set up, the crucial thing we're looking for is where does the reaction become feasible, which is the point at which delta G is 0. And this is important because at that point, delta H is equal to T delta S. So we work out entropy in exactly the same way as we did before, bearing in mind that we're then going to have to take that value and convert it into kilojoules per mole per Kelvin, so divide by 1,000, and then we can plug this into our question. So we're saying we're looking for the point at which minus 822 is equal to minus 0.2715 multiplied by T, which is the temperature in Kelvin. And if I solve that, then I'm going to get an answer of 3068, and I can say that this reaction is going to be feasible all the way up to that temperature. Finally, it's important to remember that while Gibbs free energy tells you about the feasibility of a reaction, it doesn't tell you anything about its rate. So for instance, graphite is thermodynamically unstable. It will break down, but it's kinetically stable, and therefore that process takes a very, very long time. When a reversible reaction occurs in a closed system, in other words, no matter and no energy are added or taken away, then the reaction may reach a stage called equilibrium. At equilibrium, both reactions are occurring at the same rate, and the concentration of all reactants and products in that reaction is unchanging. This does not mean that they are the same as each other, just that they're not increasing or decreasing. And in fact, there's a whole chemical industry built around trying to maximise the amount of the product while minimising the amount of reactant left over. While you can write a Kc equilibrium constant for gaseous systems, in order to do that, you need to know the volume you're working with. More typically, for gaseous systems, we use Kp, which is the mathematical expression used to describe the position of equilibrium for a reversible reaction with gaseous reactants and products. It's based on partial pressure rather than concentration. Similarly to Kc, we're putting the products on the top of the fraction, and we're also using the coefficients from the symbol equation as the powers. But differently to Kc, we're no longer talking about concentration. So brackets, if you use them, cannot be square, and we also have a P or a PP, and that can be inside or outside of the bracket. The simplest type of Kp question would just give us values for partial pressure and ask us to substitute these in. So we would end up with something like this. Like Kc, there isn't one set unit for Kp, and we need to look at the units that we've been given and the different numbers of moles on the left and right of the equation. So here we've got 4 sets of kilopascals on the top and 3 on the bottom. So once we cancel those out, we're left with an overall unit of kilopascals, but this won't always be the case. A gas will exert a pressure based on how many moles are present, regardless of the identity of that gas. Therefore, if we know the total pressure of a gas mixture and we know what proportion of the mixture each gas is, which is what we call the mole fraction, we can assign a partial pressure just to each individual gas. So if I look at the molecules that I've got, 50% of those are the red, so my mole fraction there is 5/10, but I simplify it to a decimal of 0.5, and then 20% blue and 30% green, and those are all going to add up to be 1, which is 100%. And then I multiply each of those mole fractions by my total pressure to find out that the partial pressure of the red is 75, and the blue is 30, and the green is 45. And again, those will all add up to be my total pressure. Just like with Kc, you're incredibly likely to get an equilibrium question where before you can use that expression, you need to work out what the equilibrium moles of each substance are. So you may need to construct an ICE table, or they're sometimes called RICE tables if you have ratio at the start. But I is for initial, C is for change, and then E is for end or equilibrium. A typical exam question will tell me how many moles of the reactants I started with and not mention the products at all, so we assume that they are 0. And then it will also tell me at equilibrium either that one of the reactants has changed, or it'll give me the moles of the product now. And based on this, I can work out what the change will be. So then I'm going to use that together with the coefficients in my symbol equation to work out what the change will be for the other species in this reaction. So my oxygen is only going to decrease by half a mole because that and the sulfur dioxide are in this 1:2 ratio, whereas the sulfur trioxide will also increase by a whole mole. So that gives me my equilibrium moles. But remember, at this point we're not finished. We need to convert these back into partial pressures before we can put them into the expression. So I add up the moles of all of those species, and I get a total of 5, and then I can work out a mole fraction, which in each instance I'm going to simplify to be a decimal. And then if I know what my total pressure is, then I can take that from the question and multiply it by this mole fraction to give me partial pressures for each of the substances. And then I can put that information into my expression. Remember, if they ask you to write an expression, they mean write this thing for Kp, including the names of the reactants and products in there. And then I can substitute in my numbers, and then I get a value and I can work out my units like I did before. Just like you did with Kc, you should be able to describe how changing temperature affects the position of equilibrium, the yield of the desired product, and also the value of Kp. So here I'm going to start off by saying the system shifts to counteract the increase in temperature. Then I'm going to say, well, I can see that the forward reaction is endothermic from the enthalpy value that they've given me there, and therefore that forward reaction will be favoured. That means that the equilibrium will move right, and that means that there'll be more products. And if there are more products, and remember products are on the top of my expression, then the value of Kp will increase. Then if we think about pressure, we start off by saying that as we increase pressure, the system will shift to counteract the increase in pressure. And therefore here the forward reaction will be favoured because there are fewer moles on the left-hand side of the equation. And therefore the equilibrium will move right and the yield will increase. But we now also need to think about the value of Kp. If I just throw together an expression for Kp and give you some values for a particular equilibrium, we can come up with a value for that equilibrium under that pressure. We started out with partial pressures which added up to 100 kilopascals, and therefore our initial value for Kp is 0.15 kilopascals to the -1. Now if we increase the pressure, we're going to make more of C, but you also have to remember that as well as the mole fractions adjusting, the total pressure has increased, and that's going to have an impact too. So if the pressure change leads us to having 0.1, 0.1 and 0.7 moles of each of our chemicals, and our new pressure is 420 kilopascals, then when I use the new partials, I get a new value for Kp that is still 0.15 kilopascals to the -1. So you don't really need to be able to prove this, but you do need to know that changing the pressure, although it changes the position of equilibrium and the yield of C, it doesn't change the value of Kp. Catalysts don't have any impact on the position of equilibrium, whether that's an equilibrium with solution or an equilibrium with gases that you've learned about in year 13. And the reason for this is that even though the catalyst speeds up the rate of reaction, it speeds up the forward and reverse reactions equally. So it doesn't have any impact on the value of Kp because it doesn't have any impact on the position of equilibrium. So to summarise that, temperature will change the position of equilibrium and therefore yield and Kp. Pressure will change the position of equilibrium but not Kp. And catalyst will not change either. Electrochemical cells, also known as galvanic or voltaic cells, are made of two half cells. A half cell is a structure that contains a conductive electrode and a surrounding conductive electrolyte. It isn't possible to measure the potential of a half cell, so half cells need to be examined in pairs and their potential difference calculated. In a cell with two metal-based half cells, electrons will flow from the more reactive metal to the less reactive metal, and we can use electrochemical cells to explain and predict redox reactions. You know from GCSE that oxidation is loss of electrons and reduction is gain of electrons, and you should remember that oxidation always happens at the anode and reduction always happens at the cathode. Please note this is not electrolysis, and therefore the charge of the electrodes is reversed compared to that. The most classic example of an electrochemical cell is the Daniell cell. This is made from a zinc half cell connected to a copper half cell by a wire, and through that wire electrons will flow from the more reactive zinc to the less reactive copper. In order to balance this change in charge, the free ions are going to move through the salt bridge, which is a piece of filter paper soaked in an inert solution like potassium nitrate or maybe sodium nitrate. Oxidation will happen at the anode where zinc loses electrons, and reduction will happen at the cathode where copper gains electrons. When deducing the potential of a half cell, we need to compare it to something, and this could either be the standard hydrogen electrode or another half cell that we already know the potential of. Fundamentally, we're looking at an equilibrium, so the conditions need to be standardised, otherwise this would affect the position of equilibrium. We usually think in terms of 298 Kelvin, and if the half cell involves a solution, that solution should have a concentration of 1 mole per decimetre cubed, and if gases are involved, then 100 kilopascals. The standard potential for a half cell tells you about the tendency of a species to accept electrons, and therefore its effectiveness as an oxidising or reducing agent. We can use this in order to figure out whether a chemical reaction will happen spontaneously. If we want to form an electrochemical cell or make a prediction about a redox reaction, then one of these reduction potentials is going to need to be turned around to make an oxidation potential. The rule is that we look at the e-values, and the equation that has the more positive e-value will proceed in the forward direction, whereas the equation with the less positive e-value, whether that's positive or negative, will be reversed. This then allows us to put together the two equations like so. A typical exam question will give us a list of reduction potentials, and things that are themselves being reduced are good oxidizing agents. So by looking for the most positive number, we can identify the most positive oxidizing agent. Here, that's going to be for this equation, and therefore my most powerful oxidizing agent would be the silver plus ion. Then my least powerful oxidizing agent is going to be the least positive number. So in this instance, that would be barium 2+. If we're asked instead to identify the most powerful reducing agent, then we need to bear in mind that that's going to be something that is itself oxidized. So we're looking for a species on the right-hand side, not the left, and we're now looking for the most negative number. So here, for the most powerful reducing agent, I'm going to look at this equation, and what I'm going to say is that it's barium. Then the least powerful reducing agent will be the most positive number. So again, we're back looking at this silver equation, but this time we're picking something from the right-hand side, so that's going to be silver as opposed to the silver ion. An electrochemical cell made from two half cells can be represented by this conventional representation. In this, we use a double vertical line to represent the salt bridge, and then we use single vertical lines to represent phase boundaries, for instance between these solid electrodes and these aqueous solutions. When deciding where to put the different species, we always put the most highly oxidized species nearest to the salt bridge. So in this instance, the solid metal electrodes are on the outside and the aqueous ions are on the inside. If I'm showing the representation for an electrochemical cell that is actually going to generate a potential difference, then my more positive E value is going to go on the right-hand side. When the half cell itself doesn't consist of a solid metal electrode, I may need to use platinum as a phase boundary. If I have two different species that are in the same phase, for instance two different ions in a redox electrode, I separate these with a comma. Remember, when you're assembling a conventional representation for two different equations, you need to keep the more positive one on the right-hand side, and you also need to think about the oxidation state of the different species. The potential of any half cell can be identified by connecting it to the standard hydrogen electrode, which by definition has a potential of 0. This has to be measured under standard conditions, so hydrogen gas is pumped in at 100 kilopascals with a temperature of 298 Kelvin, with usually a 1 molar solution of hydrochloric acid or another source of hydrogen ions. Crucially, it's the hydrogen ions that need to be at 1 mole per decimeter cubed. These are connected via platinum black, which provides a reaction surface to allow for a transfer of electrons. By connecting a half cell to the standard hydrogen electrode under standard conditions, it's possible for us to measure the electromotive force, which is measured in volts. If an electrochemical cell is assembled not under standard conditions, then this will affect the size of the electromotive force measured. This is why it's possible to set up an electrochemical cell that contains two half cells containing the same species, if they have different concentrations. In addition to telling us about the utility of a particular chemical cell for generating electricity, calculating electromotive force also allows us to predict whether a redox reaction between two species would proceed. In order for copper to be displaced from solution, we need this first equation to run in the forward direction. In other words, the copper 2+ ions must be reduced. A more powerful reducing agent is going to cause an E value which is more negative than the value for copper here. So we look at the numbers that are less positive than plus 0.34. And based on that, we can say that zinc, nickel and tin are all more powerful reducing agents than copper. If the overall electromotive force for a cell is higher than 0, then that reaction is feasible. But if it's less than 0, then the reaction is not feasible. In the next tier of question, we're looking for species that can start a redox reaction but not allow it to go all the way to completion. Here we're looking for reducing agents, so we need to be looking at the right-hand side of the table. And we have data for chloride ions, iron 2+ ions and zinc. We're looking for something that is a powerful enough reducing agent to reduce dioxovanadium, but not so powerful that it also reduces oxovanadium 4. So if we look to start with at our chloride ions, these are too powerful of an oxidizing agent, so they're not going to be able to reduce the dioxovanadium ions. If we look at our zinc, then that's too powerful of a reducing agent, so while it would do that first reduction step, it would also continue to reduce this down to vanadium 3+. So then we've got our Goldilocks, which is iron 2+. Electrochemical cells can be split into three types. Firstly, we divide them into chemical cells and fuel cells, and then chemical cells can be divided further into reversible cells that you can recharge and irreversible cells which you can't. In a chemical cell, the chemical reaction stops once one of the reactants has been used up. If it's a rechargeable cell, you then apply a big voltage to reverse the reaction and turn the products back into reactants so that you can use it again. But in an irreversible cell, that's not possible, usually because one of the products has then gone on to react further. In contrast to that, a fuel cell doesn't ever stop working because you're constantly supplying the reactants, and so they're never going to run out in the first place. In the AQA A-level Chemistry exams, there aren't named examples of non-rechargeable cells, but the most regularly used example is the classic Daniell cell. This isn't practical for a portable battery because it contains liquids that move around and could spill. The most common everyday cell is a zinc-carbon cell. This has a zinc case functioning as the anode, and therefore the zinc loses electrons and over time it will wear away, causing the cell to split and leak, releasing the corrosive ammonium chloride electrolyte. The cathode is a central chamber containing manganese dioxide and powdered carbon. To allow the passage of charge into it, there's a graphite rod, and on top of this is a metal lid. The ammonium chloride electrolyte is a paste with water, and that's split up from the zinc casing by a porous membrane, which allows ions to move through but not anything else. Over time, at the cathode, the second half equation takes place, which initially forms hydrogen gas, but this is quickly oxidized further by the manganese dioxide to become water, and this is why the cell isn't rechargeable. Sometimes you see the cell be slightly modified, so instead of using ammonium chloride, it uses zinc chloride, which generates a higher current and is also a longer life cell. Alkaline batteries were the named example of a non-rechargeable battery if you did AQA GCSE chemistry, and instead of having an acidic electrolyte like ammonium chloride, you have an alkaline electrolyte like potassium hydroxide. Lead acid cells are a classic example of a rechargeable cell, and they're the basis of car batteries. Usually 6 of them are wired together to make a battery with a potential difference of about 12 volts. The cell consists of 2 sheets of lead serving as electrodes, and the positive electrode is coated in lead oxide. Those 2 sheets are then dipped into sulfuric acid. At the negative anode, oxidation occurs, and 2 electrons are lost from the lead when it reacts with the sulfate ions from the sulfuric acid. At the positive cathode, those electrons reduce the lead oxide with 4 hydrogen ions and sulfate ions to make lead sulfate and water. If those processes are combined, we get this overall equation. Remember that if the cell is recharged by applying a potential difference in the opposite direction, then these processes will run in reverse. Another example of a rechargeable cell is the lithium cell. Be aware that there are several different types, but AQA only asks you about one of them. Lithium cells are very light due to the low density of lithium. They have a solid electrolyte made from a polymer which prevents leakage and the reaction of lithium with an aqueous electrolyte. The positive electrode is made from lithium cobalt oxide and the negative electrode is made from carbon. These are sandwiched around the polymer electrolyte. At the negative anode, there's a surplus of electrons due to the oxidation of lithium. At the positive cathode, reduction occurs. You are expected to have memorised the half equations for the different electrodes. Be aware that these are listed in the specification in the correct direction. Unlike our normal system where we're given 2 different reduction potentials, here the first equation has already been flipped. So that means that I then add them together to find out what the lithium cell has a voltage of, which in this instance is 4. Remember, if you're asked to give equations for recharging, you'll need to flip the half equations. You could also be asked to identify which species has undergone oxidation or reduction. The advantages of rechargeable cells are twofold. Disposing of cells is hard because they often contain toxic chemicals. Additionally, those electrolytes also contain metals that are in short supply, so by recharging and reusing the same cells, we minimise the need for mining more of these. In contrast to chemical cells, in a fuel cell a potential difference is generated by the electrochemical oxidation of a fuel, usually hydrogen or sometimes methanol. That fuel is continuously supplied. This chemical oxidation significantly reduces energy losses when compared to direct combustion. Rather than reacting directly with oxygen, the fuel is oxidized to make cations. In the most common example, hydrogen gas is pumped in and then oxidized to make hydrogen ions and electrons. Any remaining hydrogen is just pumped out again. These electrons travel through a wire. At the cathode, oxygen reacts with water and also these electrons to make hydroxide ions, and these hydroxide ions then join up with the hydrogen ions to make water, which is the only waste product. You should know the half equations for either electrode, and you should be able to join these together by cancelling out the electrons in order to make one overall equation, which is just hydrogen plus oxygen reacts to make water. You may be asked to compare the use of hydrogen or methanol fuel cells to using chemical cells. The fuel cell uses a continuous process, whereas any chemical cell can run out of fuel as it's a batch process. With a rechargeable cell, each time you charge, it stores slightly less energy, and compared to a continuous process like a fuel cell, there's a reduction in efficiency. Oxidizing hydrogen doesn't produce any toxic waste products or greenhouse gases like carbon dioxide. Part of the drive for developing rechargeable batteries is that lots of them have really toxic or corrosive chemicals in them, so the waste products may be toxic when it's time to finally get rid of them. Hydrogen is highly explosive, and this can make it difficult to store and transport. Fuel cells have a relatively low potential difference, and therefore it isn't feasible to use one single cell without making a battery. You should know 3 different definitions for acids and bases, each of which gets steadily broader. The Arrhenius definition of an acid is most similar to the GCSE one, and it's where we say that acids are substances that dissolve in water to release hydrogen ions. But the Arrhenius definition of a base is substances that release hydroxide ions in solution, and we'd recognise that as a definition for alkalis because it excludes insoluble bases like metal oxides and metal carbonates. The Bronsted-Lowry definition is the one that is introduced in this chapter, and it says that an acid is a substance that donates a proton and a base is a substance that accepts it. This means that the acid and the base don't need to dissolve, so hydrogen chloride gas reacting with ammonia can still be counted as an acid. It also depends on how the chemical is acting right now, not just what it could hypothetically do. Arrhenius acids like nitric acid and sulfuric acid can react together, and in this situation, one of them, it happens to be sulfuric acid, is functioning as an acid because it's donating a proton, but the other one, here nitric acid, is functioning as a Bronsted-Lowry base because it's accepting a proton. Now, when nitric acid accepts a proton from sulfuric acid and forms a positively charged ion, we call this a conjugate acid, and the ion that's left over is the conjugate base. We can put these together as conjugate acid-base pairs, which basically means that they've both come from the same original species. So the sulfuric acid and the hydrogen sulfate ion are one conjugate acid-base pair, and the nitric acid and the nitrooxonium ion are the other conjugate acid-base pair. The Lewis definition for an acid doesn't actually appear until the transition metal topic, but it's even more general than Bronsted-Lowry, and it is that an acid is an electron pair acceptor. This even applies to chemicals that don't interact with hydrogen ions at all. For instance, boron when it makes halides, or aluminium chloride, which is electron deficient and is able to take on a 4th chloride ion, or transition metals when they form complex ions. In addition to recalling those 3 definitions, you should also be able to describe the difference between strong acids like hydrochloric acid, sulfuric acid and nitric acid, and weak acids like citric acid, carbonic acid and the carboxylic acids. Weak acids dissociate only slightly in aqueous solution. The pH scale is a measure of the amount of hydrogen ions in a unit volume in solution, in other words, the concentration of hydrogen ions. We always give the number of pH to 2 decimal places. One whole integer different on the pH scale means a 10-fold change in the hydrogen ion concentration, because this is an exponential scale. We express concentration using square brackets, and the pH scale is a negative logarithmic scale of the hydrogen ion concentration, which means that as the numbers of the pH scale get smaller, the concentration of hydrogen ions gets higher. And also, we should be aware that the scale doesn't have a top or a bottom end. pH 7 doesn't necessarily mean neutral. It does at 298 Kelvin, but at other temperatures the pH of neutral will actually be a slightly different number. The neutral point is always wherever the number of hydrogen ions is equal to the number of hydroxide ions. In almost every question in the acids and bases topic, you'll be asked to calculate pH from hydrogen ion concentration, which we do using this formula. You might also be asked to just define pH, in which case what the exam board are looking for is you to write out this expression. When you're using this expression to calculate, on your calculator you need to either use a designated log 10 button or a regular log button and specify that the base is 10. Then whatever answer you get, you need to multiply this by -1. So if we wanted to work out the pH of a hydrogen ion concentration that was given, then we would do this like this, and as we've said, we would give that answer to 2 decimal places. But remember, it's hydrogen ion concentration you're using, not just moles. So in a particular question, you might be given or might have worked out the moles, and you might then need to divide that by the volume to get the concentration. And then you can apply that to the calculation. The second tier of pH calculations are those in which you first need to complete either a dilution or a neutralization reaction. Start by working out the moles of your initial solution, then calculate any change based on any chemical reactions and calculate the new concentration. Then go back to our original pH calculation. For a reaction featuring a neutralization, we would start off in the same way by working out our moles of hydrogen ions, then work out our moles of hydroxide ions, and work out what the excess of the hydrogen ions is. In a few minutes, we'll get to the situation if we've got an excess of hydroxide ions, because then we need some further information. I can then work out a new concentration based on that remaining excess of hydrogen ions, and then that can be plugged into my pH calculation. At all times, water is functioning as both an acid and a base, because even though water is fundamentally a covalent compound, actually it's able to dissociate into hydrogen ions and hydroxide ions. In reality, a hydrogen ion never actually stays on its own for long. Instead, it forms a dative bond with another water molecule to make an oxonium ion, or it's also called hydronium or hydroxonium. Because this is a reversible reaction and it's forming an equilibrium, we can write an equilibrium expression for this. As per usual, we've got square brackets to represent concentration and the products on the top and the reactants on the bottom. Even though water can dissociate to form hydrogen ions and hydroxide ions, and this is happening all the time, it's happening in a very small percentage of cases. The vast majority of the water remains intact, and that means that the concentration of water is much larger than the concentration of hydrogen ions or hydroxide ions. So when the equilibrium shifts, say because the temperature changes, the concentration of water doesn't even move by 1%. So there's basically no point in including it in the expression. But we can't just leave it out and still call that Kc. So instead we use a different expression called Kw, also known as the ionic product of water. And this is the same as our Kc expression, except that we've omitted the denominator. Now, if we were to look up a delta H value for this equilibrium, we would see that the forward reaction is slightly endothermic, which means that as the temperature increases, the equilibrium shifts to the right and Kw gets larger. So without any chemical reaction happening, the pH will be getting lower because there are more hydrogen ions, because more of the water molecules have dissociated. We mainly use Kw for working out the pH of alkaline solutions. This could be an unadulterated alkaline solution, such as some aqueous sodium hydroxide, or it could be the result of a neutralization reaction where the hydroxide ions were in excess. Let's say that we weren't actually given the concentration of our alkali and we had to work it out first of all. We could use the MR to work out the number of moles, and then we could put that together with the volume to work out a concentration, and then we use our Kw expression and we use the stated value of Kw. You might have learned 1 times 10 to the minus 14, but that's only relevant at 298 Kelvin, and we substitute in the concentration of hydroxide ions that we've just worked out to give us a value for the concentration of hydrogen ions, and that then goes into our pH equation. Next, we're going to think again about those weak acids. Ka, also known as the acid dissociation constant, is a specific example of Kc, but for weak acids. So as we know, a weak acid will dissolve to produce a few hydrogen ions and anions, and so we can write an expression for Ka that looks like this, or if we took a specific example like ethanoic acid, we would have our hydrogen ions and also the ethanoate ions on the top, and then the undissociated acid down below. The weaker the acid is, the smaller the value of Ka will be, and any Ka value smaller than 1 implies a weak acid, because it tells you that there is a higher concentration of the undissociated acid than of the ions that it breaks up into. Ka values are usually written in standard form because they're going to be pretty tiny. Strong acids tend not to have a published Ka value because Ka would tend to infinity, so it's not a meaningful number. Before we start using Ka to calculate pH, we're going to make 2 key assumptions. The first assumption is, provided we've got a pure weak acid that hasn't had any base or any salt added to it, then the concentration of the hydrogen ions and the anions is the same. Rather than having both of them in my expression, I can simplify it, and I can then use the concentration of hydrogen ions twice. We won't be able to make this assumption if we start looking at neutralization reactions or adding salts to make buffers. The second assumption is that because the amount of dissociation is so small, the initial concentration of the undissociated acid is constant, and I can use the value given in the question in my calculation. So a simple question would ask me to calculate the pH of a weak acid. I can write an expression like this because this is just a weak acid with nothing added to it. So I substitute in the numbers from the question, and I can rearrange this to give me a value for the hydrogen ion concentration, and that of course can go into my pH calculation, and I give the answer to 2 decimal places. pH indicators are chemicals that change colour in response to pH. When we're picking a good indicator, we want something that has a distinct colour change. Think about the fact that you would never use a universal indicator for a titration because you can't tell exactly where the colour change is. The end point is identifiable by a sharp colour change, and that occurs when you add a single drop of acid or base. The end point of the titration, where we see the colour change of the indicator, can be used as a surrogate for the equivalence point, which is where the hydrogen ions and hydroxide ions are equal. If it's a good indicator, then they will occur at the same time, but this won't always be the case. Different pH indicators change colour at different pHs, and so we use different indicators depending on what the reaction mixture is. Say a strong acid and weak base will need a different indicator compared to a weak acid and strong base. You should be able to recognise, annotate and even draw titration curves for any combination of strong or weak acids or bases being added to strong or weak acids or bases. In this example, we're adding a strong base to a weak acid. Initially, there is a sharp rise because the solution is not yet buffering. Then we see a more gradual rise in pH as the acid is in great excess compared to the base. Within 1 to 2 centimetres cubed of the equivalence point, there is suddenly a sharp rise in the pH. There's a very sharp increase in pH which is caused by the addition of 1 drop of base, and this is where we're going to find our equivalence point, right in the centre of that vertical region. Then after that there is a more gradual rise in pH as further base is added, and there's very little change in pH as the base is already in great excess. You may be asked to identify which titration curve corresponds to which reactants. So you need to think about what the pH is. For this first example, we can see that we're starting with a very strong base because we have a very high pH, and we're finishing with a strong acid that's being added because we have a very low pH. Where you have a weak acid or a weak base, of course, that's going to have less of an impact on the pH. pH buffers are solutions that resist changes to pH when a small amount of either acid or base is added. They may be acidic or they may be basic. Acidic buffers, which can buffer pHs below 7, are based on the equilibrium that happens when a weak acid dissolves in aqueous solution and dissociates to make anions. Ethanoic acid splits apart to make ethanoate ions and hydrogen ions, which I'm representing with the red rectangle. Weak acids only slightly dissociate in solution, so there is a lot of the undissociated ethanoic acid and very little of the products. A small amount of base will react to remove hydrogen ions. This affects a change in the equilibrium, so the system will shift to counteract that change, and the same number of moles of acid as the moles of base will now dissociate into anions and hydrogen ions. So the concentration of hydrogen ions is almost exactly back to where it was before, but taking into account the fact that we've got slightly increased volume. But the concentration of ethanoic acid has decreased and the concentration of anions has increased. Now let's reset back to where we started and add some acid. By adding a small amount of acid, we're adding more hydrogen ions. The system will shift to counteract that change and remove them by joining back up with the ethanoate ions to make more ethanoic acid. An acidic buffer is more typically made from a mixture of weak acid and a salt. I've added extra ethanoate ions, and there are 2 ways to do this. One is by mixing the weak acid with a solution of a salt containing the anions, such as sodium ethanoate, and the other way is to make that salt by adding a strong base like sodium hydroxide to the weak acid, which would then react to form the salt. Likewise, basic buffers are made from the weak base and a salt of that base. You should be able to calculate the pH of 3 different types of buffer and also the pH of that buffer following the addition of acid or base. For any pH buffer calculation, start by writing an expression for Ka, then identify the anion concentration and the acid concentration and use these with Ka to calculate the hydrogen ion concentration, which can then go into your pH calculation. You might see a question like this, where you have to work out the concentration based on the mass, and they often also give you the temperature, which is completely irrelevant information in this case. So we write an expression for Ka, we work out what the concentration of our salt is going to be, then we can substitute that in along with the concentration of the acid that was given in the question, and this allows us to work out a concentration of hydrogen ions, and that can go into my pH equation, and that gives me a final answer of 4.17. You could be asked to do this in reverse and work out the mass of the solid salt added. As ever, I start with an expression for Ka and then figure out where I can substitute in some numbers. So I have the concentration of the acid from the question, and I can use my pH to work in reverse and work out the concentration of hydrogen ions, which can also be substituted in. Then I can rearrange this to get an expression for the concentration of the anions, and based on that I can work out the moles of the anions, and then I need to use mass as Mr. Mole, so I would use the MR, which in this instance is given in the question, to work out a mass, which here I've been asked to convert into milligrams. Instead of a solid salt, you could be given a salt solution. This is obviously going to change the volume, and therefore you're going to need to calculate new concentrations for both the acid and the salt. So we would work out that those concentrations have both reduced, and we would be able to substitute those in again to work out my concentration of hydrogen ions, which can go into my pH calculation to give me an answer of 4.73. If you're given an acid and then a strong base, you need to think of it in terms of an equilibrium question. So start out with your full ice table, think about your concentrations to begin with, and therefore your number of moles based on that. When you add the base, think about what happens to the concentration of the acid and the salt. The salt will increase by the same number of moles as you added base. The acid will decrease by that same number of moles. So then you have moles at the end, and you can work out new concentrations of each of those. From there, you proceed exactly as you did in the previous example. The trickiest questions are those where we're then adding acid or base in a small volume to our buffer, and you need to be thinking of these as equilibrium questions and remembering that whatever you add, the equilibrium will shift to counteract that change. So hydroxide ions will react with hydrogen ions to make water, and then the weak acid will dissociate to replace those hydrogen ions. The number of moles of acid that dissociate will be the same as the number of moles of hydroxide ions that are added. So as that acid dissociates, the concentration of the anion will increase. The moles can then be converted to new concentrations using the total volume, and we use Ka to determine the new concentration of hydrogen ion and therefore pH. So for instance, here we're given a buffer solution that's made by mixing two solutions together, and then we're adding some sodium hydroxide. So we start off with our initial concentrations, and we can use those to work out moles before we add the hydroxide. When we add the hydroxide, we can work out the number of moles that have been added there, and as we add that, we will reduce the acid because it dissociates to replace the hydrogen ions that have been lost, and therefore we end up making some more anions. So we can work out the moles at the end, and then based on this total volume here, which is 41 centimetres cubed, which we need to divide by 1,000, we can work out our new concentrations. Based on that, we can then use our Ka expression, plug in the numbers we've calculated, and we can then work out the concentration of the hydrogen ions and plug that into our pH expression to give us a pH of 4.73. Likewise, when we add acid, we need to be thinking of this as an equilibrium question and thinking about how that equilibrium will shift back to the left in order to remove those hydrogen ions. So here we have a new buffer made by mixing two solutions, and this time we're adding sulfuric acid. Watch out for that diprotic acid with its two hydrogens there. So we can again start off with our starting concentrations, work out the moles, then work out how many moles we're going to be adding of hydrogen ions based on the sulfuric acid. So we've got 0.0005 of sulfuric acid, which means 0.001 of hydrogen ions. So therefore the acid is going to increase by that concentration and the anion is going to decrease by that concentration. So we can work out moles at the end and therefore concentrations at the end. Again, they go back into our Ka expression, so we can rearrange that to make hydrogen ions the subject, put that into our pH calculation and get an answer of 3.72. Period 3 are the third row of the periodic table, and the 8 elements listed in this period all have 3 shells, so their electron configuration ends with either 3s or 3p. The general trend across the period is that atomic radius decreases because all the atoms have the same number of shells and therefore shielding, but there's a higher nuclear charge, and therefore there's a stronger electrostatic attraction between the positive nucleus and the negative electrons in the outer shell. The first ionisation energy increases as we move left to right across the period due to the increase in strength of the electrostatic force between the nucleus, where we're adding an additional proton each time, and the outer shell electron, with the exceptions of aluminium, which has its highest energy electron in the 3p subshell rather than the 3s subshell where it was for magnesium, and sulfur, where for the first time we have 2 electrons sharing a 3p orbital and therefore repelling one another more strongly than the unpaired electrons. The differences in melting point as we look at the period can be explained by their structure and bonding. Sodium, magnesium and aluminium have metallic bonding, and this requires a relatively large amount of energy to overcome, and so therefore these metallic elements have relatively high melting points. Magnesium and aluminium have higher melting points than sodium because they have more outer shell electrons and also a higher charge on the cations, and both of these contribute to a stronger electrostatic force of attraction. Silicon has a very high melting point indeed because it forms a giant covalent structure. Phosphorus, sulfur, chlorine and argon have comparatively low melting points because these are held together only by weak van der Waals forces. But also we can see that sulfur as the largest molecule has the highest melting point of those four, as it has the most electrons and therefore the strongest van der Waals forces, followed by phosphorus, P4, followed by chlorine, Cl2, with monatomic argon being the lowest. The first year 13 content is about the reactions of sodium and magnesium with water. Sodium reacts very vigorously with even cold water to make sodium hydroxide, which is an alkali which turns universal indicator blue, and also a large amount of hydrogen gas, which we can demonstrate by igniting it and listening for that characteristic squeaky pop. In contrast to this, magnesium reacts very slowly with cold water. It undergoes the same process, making magnesium hydroxide and hydrogen gas, but you're unlikely to see more than a few very small bubbles. Gradually over time, if you watch a solution that's had an indicator added to it, it will slightly change colour. However, if you react magnesium with steam rather than cold water, this is a much more vigorous reaction, and it also forms a different product, making magnesium oxide rather than magnesium hydroxide. We also see a bright white light, and that magnesium oxide is a white solid. You need to know the formulae of the period 3 oxides and the observations as they form. Sodium is extremely reactive and reacts with oxygen even when it's cold, but if you do burn sodium in oxygen, it burns with a yellow flame and produces a white solid with the formula Na2O. Year 7s everywhere love to make magnesium oxide by putting magnesium in a Bunsen burner, so you hopefully remember that this makes a bright white light as it forms, and the oxide itself is a white powdery substance. The next few elements all react in similar ways. Aluminium reacts with oxygen at high temperature to produce a bright white light and a powdery aluminium oxide, which looks almost like a white smoke. This is the same extremely corrosion-resistant aluminium oxide that coats the outside of anything that's made of aluminium. Silicon also reacts with oxygen, releasing a bright white light, but only at extremely high temperatures, and often having to use something like magnesium as a fuse to start the reaction. Phosphorus will also react with oxygen to release a bright white light and a white powdery substance. It's worth noting in particular the formula of phosphorus oxide. Here phosphorus has an oxidation state of 5, and that might lead you to believe that the formula should be P2O5, but it's not, it's P4O10, because this isn't an empirical formula, it's a molecular one, so this doesn't represent the simplest possible ratio, but the actual number of atoms in the molecule. Then we have sulfur, which can react with oxygen to make either sulfur dioxide or sulfur trioxide. We discussed the importance of structure and bonding for explaining the melting points of the period 3 elements, and that's also true when we think about their oxides. Sodium oxide is ionic and therefore has a relatively high melting point because it takes a lot of energy to overcome that strong electrostatic force of attraction between the positive sodium ions and the negative oxide ions. Magnesium oxide is also ionic, but it has a higher melting point due to the increased charge density of the Mg2+ ions, which are able to more strongly attract the oxide ions, and therefore it requires more energy to overcome that attraction and melt the lattice. Aluminium oxide is ionic, but it does show some covalent character, and this can be explained by the electronegativity difference being less big, or alternatively by the small aluminium ion with a high charge being able to get close to the oxide ion and distorting the oxide charge cloud. Silicon dioxide is a giant covalent structure, and therefore it has a very high melting point due to the large amount of energy required to break the strong covalent bonds. And then our final 3 oxides are simple molecular structures with much lower melting points because it's only the weak van der Waals forces between the molecules that need to be overcome, not strong covalent bonds. The general rule of thumb is that when metallic oxides dissolve in solution, they form alkalis, whereas non-metallic oxides dissolve to form acids. Sodium oxide and magnesium oxide are both able to act as Bronsted-Lowry bases, accepting protons or hydrogen ions in order to make hydroxides. Sodium hydroxide is more soluble than magnesium hydroxide due to a weaker, strong electrostatic force of attraction between the two ions. Therefore, it dissolves more easily, and therefore it releases more hydroxide ions, and this leads it to have a higher pH, even if they're the same concentration, and even though magnesium hydroxide is still alkaline. Aluminium oxide and silicon dioxide are basically insoluble, so they don't affect the pH. And then phosphorus oxide and sulfur dioxide and sulfur trioxide can all dissolve to produce different acids. Phosphoric acid forms when 1 mole of phosphorus pentoxide reacts with 6 moles of water. This phosphoric acid can then dissociate in water to form dihydrogen phosphate ions. Sulfur dioxide can react with water to make sulfurous acid with the formula H2SO3, whereas sulfur trioxide can react with water to make the more familiar sulfuric acid. You also need to be able to explain using symbol equations how these acidic oxides react directly with bases, like this phosphorus pentoxide reacting with sodium hydroxide. Now these can be a little bit challenging to remember, and I personally find it helpful to imagine that you're dissolving it to make an acid first. So we know that 1 mole of phosphorus pentoxide will react with 6 moles of water to make 4 moles of phosphoric acid. So if I now take those 4 moles of phosphoric acid, I now have a standard acid-alkali reaction, where 1 mole of hydrogen ions combines with 1 mole of hydroxide ions to make 1 mole of water. So my phosphoric acid reacts here, and we make the salt and also the 12 moles of hydrogen ions and the 12 moles of hydroxide ions, which come together to be water. If we join together this equation with the previous equation, then we're left with something like this. And what we can see now is the 6 moles of water I added at the start that aren't really supposed to be in the equation are being balanced out by some of the 12 moles of water that I make. So I can just cancel those out, and we're left with the final equation in which 1 mole of phosphorus pentoxide reacts with 12 moles of sodium hydroxide to make 4 moles of salt and also 6 moles of water. We can also express this in an ionic equation, which looks a bit like this. The equivalent equations for sulfur dioxide and sulfur trioxide are much more straightforward. 1 mole of either gas reacts with 2 moles of sodium hydroxide to make a mole of salt and a mole of water. Sulfur dioxide forms sodium sulfite, or to give it its proper IUPAC name, because AQA will, sodium sulfate 4, where the 4 represents the oxidation state of sulfur in the SO3 2- ion, and sulfur trioxide forms sodium sulfate, or sodium sulfate 6. Again, we can also write ionic equations for each of these in which we skip the sodium spectator ions. You first met silicon dioxide in GCSE chemistry, where it was an example of a giant covalent structure or a macromolecule. So you already know that it contains thousands of atoms covalently bonded together, and this makes it very hard, gives it a very high melting point, makes it very unreactive, and also makes it almost completely insoluble. However, chemists love to classify things, and so we want to be able to call it either an acidic oxide or a basic oxide. Now, silicon dioxide won't react at all with water or dilute alkali, but it will react with very concentrated alkali, and therefore we do classify it as an acidic oxide. Aluminium, as ever, is the complicated one. Aluminium oxide is amphoteric, which means that it can act as either an acid or as a base. You need to be able to write symbol equations for aluminium oxide acting in both ways. So to give you an example of it acting as a base, here we have it reacting with hydrochloric acid to make a salt and water, and again we can write this as an ionic equation if we omit the spectator ions. Then it can also act as an acid, so here we have aluminium oxide reacting with sodium hydroxide to make sodium aluminate, which is what was made during the hydroxide precipitation test to identify the cations. And again we can put that as an ionic equation as well if we omit the spectator ions. Finally, your 2 basic oxides will both react with an acid in order to make a salt and water. You should be prepared to write a full chemical symbol equation for them reacting with any of the major strong acids, or write an ionic equation in which you skip the spectator ions. AQA define transition metals as elements with an incomplete D sublevel in either the atoms or the ions. At GCSE, we treated the entire D block as the transition metals, and these are the elements that have their highest energy electron in a D subshell, but at A-level we refine our definition. Elements from scandium to nickel have an incomplete D subshell in their atom, so they're clearly transition metals. Then copper has a full D subshell as an atom, but when it forms 2+ ions, these only have 9 D subshell electrons. Zinc is not a transition metal, as both its atom and its ion have full D subshells. The 4 key properties that you need to recall for transition metals are that they form complexes, they form coloured ions, they have variable stable oxidation states, and their catalytic activity. A complex ion contains a central metal atom or ion surrounded by a number of ligands. These are molecules or anions that donate a lone pair of electrons, and this is equivalent to a dative bond. We can describe the number of bonds in terms of the complex ion's coordination number. Note this is the number of bonds formed, not the number of ligands, as some ligands can make more than one bond. When you draw the complex ion, you should ensure that the lone pair that's bonding from each ligand is visible. Arrows go towards the central metal species. The square brackets demonstrate that the charge applies to the whole ion, not just the central metal species. This hexa aqua copper 2+ ion has a coordination number of 6. Ligands can be both neutral molecules or anions, they just need a lone pair of electrons. They can be classified according to the number of bonds they make as monodentate, bidentate or polydentate. Water and ammonia are monodentate ligands of similar size and no charge, which can replace one another in substitution reactions. You might expect 6 ammonia molecules to replace 6 water molecules, but this is incorrect. Instead, we only see partial substitution with 4 ammonia molecules replacing 4 of the water molecules. A chloride ion is a larger ligand, and 4 of these will replace 6 water molecules. This leads to a change in coordination number. It also changes the overall shape of this complex from octahedral to tetrahedral. And this is accompanied by a colour change from blue to a vibrant green. Similar reactions also occur with complex ions containing cobalt and iron. You may need to write equations for the substitution reactions and explain how the different size of the ions leads to a change in shape. So here, chloride is a bigger ligand, so only 4 ligands can fit around the metal ion. You should specifically know about heme, which is an iron 2 complex with a multidentate ligand. Oxygen forms a coordinate bond to the iron 2 in hemoglobin, and this enables oxygen to be transported in the blood. Carbon monoxide is toxic because it replaces oxygen coordinately bonded to the iron 2 in hemoglobin. Cyanide and thiocyanate ions are not named examples in the specification, but they do appear quite frequently, so it's worth being aware of their existence and that they're monodentate. The 2 bidentate ligands you should be able to recognise and draw are the ethane dioate ion, also sometimes known as oxalate, and the ethylene diamine molecule, which is abbreviated as EN in sketch diagrams. For each of these, you should be able to recognise and draw the ligand, as well as identifying the lone pairs that allow it to bond. EDTA, or ethylene diamine tetraacetic acid, is a polydentate or multidentate ligand that forms 6 dative bonds, using nitrogen and oxygen atoms with lone pairs. You should be able to write substitution reactions for any of these bidentate or polydentate ligands replacing the monodentate ligands in a complex. We learned in the thermodynamics topic that in order for reactions to be feasible, either they need to be exothermic with a negative enthalpy change, or they need to cause a large positive increase in entropy. When a bidentate ligand such as ethylene diamine replaces a monodentate ligand such as water, 4 particles, the 3 ethylene diamine ligands and the 1 original complex, are replaced by 7, the 6 substituted ligands and the 1 new complex. This increase in the number of particles increases entropy and makes the substitution extremely feasible, and we call this the chelate effect. Likewise, here we can see ethylene diamine replacing 6 ammonia ligands. The entropy change is large and positive, so the change in Gibbs free energy is negative and the reaction is feasible. The next part of the topic is shapes, and unlike the AS bonding topic, we only need to remember 4 shapes. Octahedral ions like hexa aqua ions have a coordination number of 6, and this could be caused by 6 monodentate ligands, 3 bidentate ligands, or 1 hexadentate ligand, or a combination of them. If there's more than one type of ligand, then this can lead to isomerism. If the ligands are monodentate, then it's possible for the complex to show cis-trans isomerism, depending on whether the ligands of the same type are adjacent or not. If the ligands are bidentate, then it's possible to have optical isomerism. These optical isomers, or enantiomers, are mirror images of one another. As you know from your organic chemistry, these are going to respond differently to plain polarised light, in that one of them will rotate the light one way and one of them will rotate the light in the opposite direction. When chloride ions replace water molecules in a hexa aqua ion with copper 2+ or cobalt 2+ or iron 2+ at the centre, or when they replace ammonia molecules or hydroxide ions, then their larger size means that only 4 ligands can surround the central metal ion. This leads to a tetrahedral complex. Square planar complexes are also seen where there are 4 bonding ligands, but usually only when the central ion is nickel or platinum or silver. The one named example is the platinum-2 complex cisplatin, which is used as an anti-cancer drug. As the name would suggest, it's the cis isomer. There is also a trans isomer where the chloride ions are on opposite sides of the complex. Cisplatin prevents DNA replication in cancer cells by a ligand replacement reaction with DNA in which a bond is formed between platinum and a nitrogen atom on guanine. Even though cisplatin is a medicine, it can still cause damage to healthy non-cancerous cells as it may attach to the DNA in those cells too. However, the benefits outweigh the risks when somebody has cancer. The final shape that you need to know about for complex ions is linear, and a good example of this is Tollen's reagent, which you encountered as a test for aldehydes. Transition metal compounds have characteristic colours. At GCSE, you met the sodium hydroxide precipitation test, which gives a dark green iron 2 hydroxide precipitate, a rusty orange-brown iron 3 hydroxide precipitate, and a blue copper 2 hydroxide precipitate. Solutions appear coloured due to the way they absorb certain wavelengths of white light while transmitting other wavelengths. This is because within the atom, d electrons are able to absorb light of a specific wavelength and move to a higher energy state, but they can only do this if the d subshell is incompletely filled. We can calculate the energy change for this process by using Planck's constant. Transition metal complexes may change colour due to changes in oxidation state, coordination number, and the ligand, because all of these will change the amount of energy absorbed. The coloration of these complexes can be used to identify the concentration of a solution using a colorimeter. White light is shone through the sample and the absorbance at a particular wavelength is detected. Samples of known concentration are used to generate a calibration curve, and the sample can then be compared to that curve to work out what its concentration is. Transition metals are well known for having multiple stable ions with different charges due to their multiple stable oxidation states. An oxidation state is a number that we use to represent the number of electrons lost or gained by an atom of an element when it forms a compound. As you can see, all of these transition metals have multiple stable oxidation states, with the ones in bold being the most stable of all. Vanadium is a classic example, and it has 4 stable oxidation states, which you should be able to identify in neutral compounds as well as in ions. Vanadium can be reduced from an oxidation state of +5 to +2 by a reducing agent such as zinc or aluminium, and you need to be able to write half equations for each step of this process. So it helps to be able to work out what the oxidation state of vanadium is in a particular complex ion. Yellow dioxovanadium ions contain 2 oxygen atoms, each with an oxidation state of -2, and this taken together with vanadium gives the complex ion an overall charge of a single positive, so therefore the vanadium has an oxidation state of +5. To make blue oxovanadium 4 cations, we've got 1 oxygen now, which still has an oxidation state of -2, and the whole ion has a charge of 2+, so therefore vanadium has an oxidation state of +4. Now, in order to make this half equation balance, I need to think about the charges and the oxygen, any hydrogen, any electrons. So here I can see that in order to make the oxygen balance, I'm going to need to add a water molecule. And then in order to make that work out, because I've of course added 2 hydrogens as well as an oxygen, I'm going to need to add 2 hydrogen ions. And then to make the charges balance, I add a single electron, which also helps to sort out the oxidation states. If we use zinc as our reducing agent, when zinc is oxidised, it loses 2 electrons to form Zn2+ ions. But I can't join these 2 half equations together if the electrons don't balance. So first I need to double up my first equation, and then that allows me to cancel out the electrons in each of these equations. If I join these together, then I then get an overall equation which looks like this. Likewise, you should also be able to write ionic equations for each of the subsequent reduction steps. If you're wondering why transition metals exist in different oxidation states at different time and there isn't a single most stable version, it depends on the conditions they're in and also the ligands they're bonded to. So in general, acidic conditions favour reduction and alkaline conditions favour oxidation because they're going to affect the position of the equilibrium. You need to be aware of the use of Tollen's reagent to distinguish between aldehydes and ketones. To make the tolerance reagent, we take some silver nitrate solution and add a tiny amount of sodium hydroxide, which makes it slightly alkaline, and that causes a precipitate of silver oxide. You then add enough dilute ammonia to redissolve that precipitate, and you make this diamine silver ion. Now, because the solution is alkaline, it's possible for this aldehyde to be further oxidized to make a carboxylic acid, or at least to make a salt of the carboxylic acid. And that doesn't happen if you've got a ketone because it can't be oxidized any further. So as the aldehyde becomes oxidized to make the carboxylic acid, the silver is going to be reduced. And in picking up an electron, the silver ion within this diamine complex is going to turn into atomic silver, which isn't soluble. So therefore we get a precipitation and we get this lovely silver mirror. Titration is an analytical technique where we use the concentration of one substance which we do know to work out the concentration of a second substance which we don't. Unlike an acid-base titration, a redox titration doesn't require the addition of a pH indicator because these titrations are self-indicating. We're adding either a reducing agent or an oxidizing agent, and then based on the oxidation state of the transition metal present in the reaction, as it changes oxidation state, it changes colour, and therefore the reaction self-indicates. Manganate ions are frequently used as a redox indicator because potassium permanganate is this really vibrant purple colour, but as the manganese is reduced from +7 to +2, it becomes colourless. In order for this reaction to proceed as it should, the potassium permanganate needs to be acidified using sulfuric acid. If we don't have acidified conditions, then the reaction won't proceed as it should, but also we may form manganese dioxide, which is a black or dark brown precipitate. The choice of acid is also important. A weak acid doesn't provide sufficient hydrogen ions. Hydrochloric acid contains chloride ions, and these are oxidized by the manganate ions, and that means we would end up adding too much manganate. Likewise, nitric acid is itself a good oxidizing agent, and so if we use that, we end up adding too little manganate. Manganate ions are regularly used to identify the concentration of iron in products such as iron tablets, but also vegetables like spinach or thyme. We can also use manganate ions in order to identify the concentrate of ethane diorate ions. This occurs in the same way as with the iron 2+, so we have that same colour change where we start off with a colourless solution, and then when the potassium permanganate is in excess, it stays purple. But one thing you should note with this reaction is that because both the manganate ions and the ethane diorate ions are negatively charged, they will repel each other, and therefore the reaction is slow to begin with, and so it has to be heated to about 60 degrees. But once it gets going, this is an autocatalytic reaction, and therefore it speeds up on its own. Transition metals and their compounds can act as catalysts both when they are in different phases to the reactants and when they're in the same phase. Catalysts are chemicals that speed up the rate of a reaction without being used up or changed themselves in a permanent way. They do this by providing an alternative pathway with a lower activation energy. Not every transition metal is an appropriate catalyst for every reaction. How effective a catalyst is will depend on how strongly it makes temporary weak bonds while changing oxidation state. While changing oxidation state, transition metals easily gain and lose their 4s and 3d electrons, allowing them to make weak bonds. We commonly see solid transition metals or transition metal compounds used as catalysts for reactions in which the reactants are either gases or aqueous solutions. The way in which the transition metal reduces the overall energy requirement for the reaction is by breaking it down into a number of smaller steps, which occur at active sites on the surface. Remember, that term doesn't just apply to enzymes. The key parts are adsorption, in which the reactants adhere to the surface of the transition metal, bond breaking and making, followed by desorption, in which the transition metal lets go. Very often the transition metal will be milled into tiny particles which are then applied to a support medium in order to maximise the surface area and minimise the cost. Vanadium pentoxide is used as a catalyst in the first step of the contact process, which is used to make sulfuric acid. We take vanadium with an oxidation state of +5 and it's reduced to an oxidation state of +4 in the formation of sulfur trioxide. Then this comes together with some more oxygen to restore the original vanadium to its +5 oxidation state. Platinum and the other platinum group metals are commonly used in catalytic converters in vehicles in order to reduce the production of carbon monoxide and also oxides of nitrogen. But these catalysts can easily be poisoned by lead or sulfur impurities, and this makes it necessary to remove these from fuel. You should also know that iron is necessary as a catalyst in the Haber process in order to reduce the energy requirements. In order to prevent the poisoning of catalysts, which reduces the efficiency of the catalysts and therefore has cost implications, reactants need to be purified before they come into contact with them. There are also many examples where the reaction between two ions in aqueous solution is catalysed by the presence of a transition metal ion or a transition metal compound ion. This is particularly likely to be the case where you have two anions reacting, where because they both have a negative charge, they're repelling each other, giving the reaction a very high activation energy. But if a positively charged transition metal cation is present, then both of the ions are attracted to this, and therefore the reaction can occur via this intermediate. So in this example, the iron 2+ ions act as a reducing agent and reduce persulfate ions to make sulfate ions, and this leads to the production of iron 3+. But then that iron 3+ acts as an oxidizing agent and oxidizes iodide ions. So we get back the original iron 2+ ions, and we also have some iodine produced. So if we remove the catalysts from this, then we get an overall ionic equation in which the iodide ions react with the persulfate ions to make sulfate ions and iodine. It's also possible for a transition metal ion to be catalysing a reaction in which it's made, and we call this autocatalysis. We can identify it by looking at a graph of concentration over time, because to begin with the reaction proceeds quite slowly, but then it speeds up, which is incredibly rare because collision theory tells us that as reactants are used up, we would expect a reaction to slow down. But what's happening here is that as the product is made, that acts as a catalyst and speeds the whole thing up. An example of an autocatalytic reaction is the oxidation of ethane diuric acid by potassium permanganate. To start with, we have manganese in two different forms: the monatomic ions with an oxidation state of +2, and also the manganese with an oxidation state of +7 in the permanganate ion. Because the permanganate ion is reacting with ethane diuric acid, this is under acidic conditions. In doing this reaction, the monatomic manganese ions are going to be oxidized to 3+ ions, and those 3+ ions are then going to be able to interact with the ethane diorate anions and return the manganese to a +2 oxidation state, also producing some carbon dioxide along the way. In order to discuss the reaction of ions and aqueous solutions, you need to be comfortable with all of these definitions, which we've met earlier in paper 1. The first specification point in this section is about different coloured complex ions that form when certain metal compounds dissolve in water. They're all these octahedral hexaaqua ions with 6 water ligands surrounding the central metal ion, so all you really have to remember is the charges and the colours. We have the bright blue copper 2+ hexaaqua ion that you see in copper sulfate, the green hexaaqua iron 2+ ions, then there's a colourless hexaaqua aluminium 3+ ion, and also the hexaaqua ion for iron 3+. You've met that as a sort of orangey brown rusty coloured substance, but also under certain circumstances it can also form its monohydrate type, and then it's a sort of pale lilac-y violet colour. The specification includes examples of complex ions that are 3+ and 2+, because they want you to have this idea that the 3+ ions like aluminium and iron 3 have a greater acidity than the 2+ ions like copper and iron 2. The reason for this is because those 3+ ions have a greater charge and therefore a greater charge density. This means that they have greater polarising power. So they attract the water molecules more strongly, and in doing so they weaken the OH bond in the water molecule so that it breaks more easily. When that happens, 3 hydrogen ions are released, which are responsible for the acidity. In terms of reactions, all the specification says at this point is that you need to be able to describe and explain the simple test tube reactions of M2+ and M3+ ions with the bases hydroxide, antimony, and carbonate. If we think firstly about the addition of hydroxide, this is the same reaction that you met at GCSE if you took triple science. If you add sodium hydroxide to a source of copper 2+ ions, then you're going to see a blue precipitate. If it's iron 2+, then we see a dark green precipitate. If iron 3+, then we see an orangey brown precipitate. And if we have a source of aluminium ions, then it forms a white precipitate, which will redissolve if you continue adding sodium hydroxide. If you add limited ammonia, you get the exact same reaction, not just something that looks the same, but literally the same chemical reaction. This is because the ammonia acts as a Bronsted-Lowry base. It joins up with the hydrogen ions from the water to make ammonium ions, leaving behind a surplus of hydroxide ions, which then behave in exactly the same way. To make this slightly more complicated than GCSE, we now write symbol equations with state symbols. For hexa-aqua copper 2+, or hexa-aqua iron 2+, one of the 6 water ligands is replaced by a hydroxide ion. Then another hydroxide ion does another bit of substitution, and we're left with this solid precipitation. This is a partial or incomplete substitution. You're not going to see all of the water molecules being replaced. We can summarise this by joining together the 2 steps to make a single equation. Alternatively, ammonia will take 2 hydrogen ions away from 2 of these 6 water molecules, and what we're left with is that same precipitate alongside 2 ammonium ions. Aluminium is the interesting one of these ions because if we take those aluminium ions and add a source of hydroxide ions, then we get this white precipitate that you can see here. But if you keep on adding hydroxide ions, then eventually the white precipitate redissolves and it makes a colourless solution instead. The hydroxide also reacts with acids. If we have a source of hydrogen ions, then we can turn it back into that hexa-aqua aluminium ion that we had at the very beginning. Since aluminium hydroxide reacts with both acids and alkalis, we call it amphoteric. So limited ammonia will break apart some water and leave us with this incomplete substitution where 2 of the water ligands are replaced by hydroxide ions and we get an overall uncharged precipitate. But if we continue to add excess ammonia, then a further substitution will take place. 4 ammonia molecules replace the 2 hydroxide ions and also 2 of the water molecules. So what we're left with is a different incomplete substitution. The 2 water molecules are as far apart from each other as they can be, and then also the 4 ammonia molecules make up this tetraamine diaqua copper 2 complex ion. This is accompanied by quite a vibrant colour change to this really dark, deep blue solution. Next on the list of test tube reactions is the reaction of 2+ ions with soluble carbonates like sodium carbonate or sodium hydrogen carbonate. In each instance, rather than forming a complex ion with 6 water ligands, the metal ion joins with the carbonate anion and the 6 water molecules are kicked out and left over. This leaves a precipitate to form. The reactions of the 3+ ions are slightly more complicated than the reactions of the 2+ ions, but it helps if you remember that the 3+ ions behave more like acids due to their greater polarising power because of the higher charge. If you think about how an acid would react with a carbonate, you know it makes a salt and carbon dioxide and water, and that's exactly what's happening. So if we've got some aluminium hexa-aqua ions, to start with they have these 6 water molecules, and 3 of those water ligands are going to dissociate to make hydroxide ions and hydrogen ions that can then go on and join up with some of the oxygen from the carbonate ions to produce some carbon dioxide and also some water. So what we observe is a little bit of effervescence and then also the precipitate. For aluminium this is going to be a white precipitate, and for iron 3+, it's a sort of orangey rusty brown precipitate. Thanks for watching and congratulations if you actually made it to the end. I hope that you're now feeling a bit more prepared for A-level Chemistry Paper 1, and if you have found this useful, don't forget to like and subscribe for more A-level Chemistry content coming soon.